have Naja and Muhammad. Okay, let's just start like the same time. Okay. First of all, what you did on drawing the BNID with your hand. Started with Naja. 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 Muhammad.
Yes, doctor.
Yes, what you did in your assignment or drawing the BNID with your hand. Do you have any comments? Did you do it?
Three-phase separator, what you told, three-phase separator.
Yes.
Completely gone through each and every detail. I'm ready to explain everything on this.
Can you give a picture for us? Send it on WhatsApp.
Okay, I'll give you a little bit while. Yeah.
Okay, Muhammad.
Yes, doctor, yes.
Good morning, Muhammad.
Good morning, doctor.
Did you make the 3D?
Yes, but to be honest with you, I couldn't just like draw it by my hand because I tried, but it was difficult. My drawing skills is not that good. So I just like highlighted in different colors for each system, okay? So I follow it and do it just like we can say in good way. But I have just like a question, please, regarding it. If possible, we can discuss it.
Yes, tell me.
Thank you very much. I've noticed that at the beginning, before entering the three-phase separator, the shutdown valve is just like there is a bypass with the valve, which is okay, while in the vent of the separator itself, the ESD number 4005.
Let me open the BNID and share. Can you open it from your side?
Let me just like. Okay, so you can see it, doctor?
It is loading.
My screen is okay with you?
No.
Okay.
Naja, do you see it? Naja, do you see the Muhammad screen? Yes, it's coming now, Muhammad.
Yes, yes.
Okay, start, Muhammad. Tell me.
So I will use just like pen or something like this. So for this one, so it is equipped with just like bypass and these valves, okay? While the one in here is this one with double block and bleed.
Yes.
Okay. For products, so there is nothing just like comes with the ESD. Yeah, this is for this stream.
Yes, and for the liquid light, for the condensate light.
Yes, yeah. And this one as well, yeah, this one. So I
Yes.
just wanted to, why the difference in the arrangement or configuration of ESD in eStream? What makes the difference, please?
What's your philosophy?
Here is just like the isolation should be I, right? And sectionalizing philosophy, right?
Totally right.
Yeah.
The question is why we have ESD with a bypass as the inlet, ESD for the gas without bypass, the same for the liquid. Did I get your question right?
No, to be honest with you. So, what it depends on, please?
Depend on the philosophy you're drawing it.
Okay.
There is, let me remember this company. There is a company called the Dragon Oil in Emirates. They have two plants, one in Kazakhstan and one in Egypt. Both plants don't have the ESDs for the gas, for the condensate, for the water. They only depend on control valve. Is that wrong? No, it is not wrong. It depends on their philosophy in designing this. They don't want to invest more. They accepting high risk compared with others. In this case, can you accept my request?
Okay.
In this case, what I was trying to do, I want to do for a black startup, I want at this point if we start our plant or start our well, the problem will be that the gas will come here at this side of the ESD valve, at this side of the flange, and it will be like 900 psi, where the pressure in all the vessel will be still zero. So for a black startup, which is a mode of operation you have to consider during the design, during the operation manual, we make this bypass. Why? So the operator during the startup, he can use this bypass to pressure up the separator inside here, to build up the pressure here, to raise the pressure here. Okay,
Okay.
that's one. Let's go for the other. For the gas side, what I was trying to do, I trying to make sure that this blow down valve will have certain volume in case of fire, which mean I will need to have this ESD in case of fire to be closed, this ESD in case of fire to be closed, and this blow down to open in case of fire to vent or relieving all the gas here to the flare. So a typical configuration for the blow down is as you see. Valve before, valve after, vent, and RO. And all this operating by SESD signal, which is interlock 1. We will see the cause and effect today, and how interlock 1 initiates the ESD in case of fire and send the signal here to this blow down valve to the solenoid, from the solenoid converted back to instrument air to open this blow down valve to relieve all the gases inside the separator to the flare. Your question was why we have a manual valve here and manual valve there and vent. Because blow down valves, due to high pressure at this side and almost zero pressure at this side, sometimes suffer from leakage, or sometimes the valve is not completely isolated, so we need to make a maintenance for it. This can be done by closing this one valve, manual valve, closing this manual valve, and get this ESD out to be maintained. This is one of the cases we can use it. The good question is, should we use it? Yes and no. Yes, in case of maintenance, normally, or no, this valve is open, this valve is open, and the ESD is closed. Can you see here? Fail open. Fail open valve mean when there is no electricity, no instrument air, this valve position will be open to make sure that all the inventory, all the gas inside the separator will go out. You got my point?
Yes, doctor.
Compared with others, let's go down. We take the gas 1. As long as this separator has 3 outlets, I will need 3 ESD valves. 1, 2, 3. All fail close, as you can see. FC, FC, FC. All the same are fail close. All the 3 are fail close valves. So in case of emergency, in case of electrical disconnection, or there's no instrument air, all the 3 valves will closes, and only the blow down valve will be fail open, FO. And here on the other side, the inlet also will be fail close. So I isolate this inventory. Here. You got my point, Muhammad? Now,
Yes,
this
yes, doctor.
inventory are isolated from the inlet and all the outlet, and it will be depressurized through this blow down valve. So when I calculating the amount of gas will be depressurized from this blow down valve, I will take the separator and this piping volume from the inlet, outlet, liquid condensate, and even the liquid water. And this one also. That's why this configuration is compared with other. I love this configuration. On other words, there's some process engineer will not do the same. Will not do the same. They simply can put this ESD valve on the other PNID as the inlet of the surge drum. They can put this. They cannot even not putting this ESD valve. They will depend only on this control valve. All of this configuration depend on which philosophy you are applying. Which philosophy you are applying. Typical separator as per API 12G, you will have only one ESD here, one pressure control valve here, and all of this is a normal level control without ESD. Why we put all of this? To make sure that we are making our post. So in HAZOP, which we did last day, you will see that there will be no more recommendations. There will be at least 2 layers of protections for each part. You got it or no, Muhammad?
Yeah, thank you, brother. Thank you, doctor. Doctor, you usually use inventory as well. So what does it mean in terms of process context, please?
Inventory means this equipment volume, this piping 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 volume. Why we are saying this piping volume? Because next day, inshallah, last day, we will make the calculation for this blow down valve, for this pressure safety valve. According to API 521, what we want to do, or what we want to make sure about it, the sizing of this blow down valve will be more than enough to depressurize all this equipment, all this volume, all this inventory to half the design pressure or 7 bar G in 15 minutes. You got my point? You got my numbers? Half,
Yes,
half that is the design. Half the design. If it is designed to be 1440, the least you can go to until 700 psi. If it is designed for 1440 psi, you can go for 700. This is one of the cases we can do it. On the other hand, or 7 bar G. So if this one is operating at like 1000 psi, 900 psi, you have to depressurize it till it reach 100 psi, which is equivalent to 7 bar, in 15 minutes. The API tell you to select the minimum. Between the 7 bar and the half of the design. Based on that, you size the blow down valve to make sure that it will depressurize in less than 15 minutes. we will do it by numbers last day, inshallah. Okay?
Yeah, okay, doctor. And that's why there is a blowdown valve and PSV, because we, in case of emergency, we need to just like vent the vessel with, as you said, within 15 minutes, which is cannot be done by PSV. But PSV, just like in case there is an increase in the pressure, it can just like vent it. So for this reason, we need both when we just like for any pressure vessel, right?
Any ASME pressure, it is a must for ASME pressure to have a pressure safety valve. Okay?
Yes.
This one. Second one is adding blow down valve will help you to depressurize all the gas here in case of fire, in case of any problem. You shouldn't have to wait until the fire build up the pressure inside the separator, increase the temperature of the metal, which increase the condensate temperature, which evaporate more gas till it reaches the setting of the pressure safety valve. So blow down valve is considered one layer protection. It is a shield against the fire, and pressure safety valve is another shield. If normally you shouldn't reach the pressure safety valve case in emergency situations. What is normally happen if, for example, if you have a fire case, your fire detector will detect that there's some fire here, so it will send interlock signal. Here is the 1, 2 for the liquid, 3 for the condensate down, and 4 here for the inlet. It will close. Tuck, 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 tuck. 4 closes. 5 open. Here. Please open this blow down valve. That's normally what you are trying to have in the cause and effect. The question is, what happens if there is power cut and you have a fire? You got my point, Muhammad?
Yes.
Naja, are you following?
Yes.
Perfect. In case of power cut, this valve will be close. Right?
Yes.
And normally this one will be open. This means even in power cut, we are securing ourselves in case of fire. But there's some optimistic people telling you that what happened if the case is you close this one in case of fire and in case of electrical disconnection and there is no electricity. This one will be closed, this one will be closed, this one will be closed, this one will close, and this one is refused to respond. You got my point? The first case is the normal case, which all these 3 are closed, 4 closed, this normally open. But
Yes.
one of the people coming telling you that what happened if this blow down valve didn't respond, didn't refuse to open. So what you should do, Muhammad, you should wait until the fire finish, then you go to check this one, or you depend on your last layer of protection, which is the pressure safety valve. So you will go to the pressure safety valve. That's why when we are sizing the pressure safety valve, it will be the same size as the blow down valve in as a rule of thumb, but not in all cases. Let me make zoom in to make sure see the difference. As you can see here, this pressure safety valve is sitting at 1360 psig, which is the maximum for carbon steel rating 600 according to ASME B31.3. ASME 8 division ASME division 8 B31.3. As you can see here, the blow down valve. Here, the nozzle size is equal to the same nozzle size here, and the pressure safety valve here, the two are sitting at 1360 psig, and here this one didn't have any setting. It is only working on the signal coming from the interlock for the ASD. Is it clear for everyone? Yes or no?
Yes, thank you. It's clear. But if possible, just like if you can explain, please, the idea or give just like overview about the interlock. So how just like it sends the signal, how this system works, if possible, please.
We were going through the cause and effect and making
Inshallah.
making by yourself.
Inshallah. Okay, thank you.
You're welcome. Naja, is it clear for you?
Yeah, clear.
Okay, let's try to make the cause and effect now. To continue this part, then we will go to the pump hydraulic. Okay?
Okay.
Let me open the cause and effect. It is on your WhatsApp. It is the same folder we said it before. Just I will open it from my side. Can I take control, Muhammad, please?
Yes.
Can you just stop sharing and I will share mine? Is it clear for everyone?
Yes.
Not yet, doctor. Yes, now it's coming.
Okay. I will just stop on this one and share this one and let's think loud. Okay. The way of thinking. Can you all make mute, please? Yes, thank you. The way of thinking. How we are thinking about the cause and effect, and how should the cause and effect be drawing, and why. Let me print my board so I can write on this one. Okay, let's make it draw. Okay. Let's see. From the feed study, from the field study, we was understanding that there is some philosophy we write it. One was the isolation philosophy. Two was the isolation philosophy here, isolation philosophy here, isolation philosophy here. At the skid entry level, there was a drain philosophy. That's why we make this configuration. There was a relieving philosophy. That's why we make all this configuration. This is why we have also there was sectionalization. That's why we have this one, and this one, this one, this one. 5. Control and operation. That's why we have this level control valve here and there. That's why we have this control valve, pressure control valve, which is coming under control and operation philosophy. That's typically 5 or 6 philosophies that's what we have during the feed, and we wanted to update them or implement them on the P&ID. What's coming normally is isolation philosophy. Let's start with it. Our philosophy was saying that we need a double block and a plate for every high pressure, low pressure interface. That means in some cases when there is high pressure here and low pressure here in the pipeline, we will need a double block and a plate, which will be valve, another valve and a plate on it. This is one of the positive isolation. This is one of the client requirements. That's why in the first day we're speaking about the isolation, the way we are thinking when we are making a P&ID. This is the high pressure, low pressure. You can see. Let's give some examples. A valve with a blind is considered, with a spectacle, is considered as a positive isolation. If you want to isolate this one, this equipment overall, you will simply close the valve and switch the spade. So you will have 2 layers of isolation. Same here for the outlet gas. A valve, only one valve here for the outlet condensate, and another valve for the outlet water. And even the drains header, we have the same valve with the spectacle, the same valve with the spectacle, the same valve with the spectacle. The good part we have is, did you see this dash line? This dash line is coming, or is called the interface between our stream, our scope, and vendor scope. Some vendor will going to provide this separator, and the separator can, yes, tell me.
Sorry, doctor, for interrupting.
No.
So this is the dotted line. Yeah, thank you. So this is the dotted line. It represents the just like vendor and just like the other contractor may be line. Because I thought it, to be honest with you, I thought it is just like the boundary of the separator itself. So this
Yes,
is
it is
not.
the boundary of the separator. It is the package limit. That's represent what is coming from the vendor on the skid to your site. Here is the limits.
Okay. So in terms of isolation of the separator itself, so I should just like close the valve within this boundary, or just like straight away after the inlet and outlet of the separator, please.
Okay. Every
Thank you.
every vendor want to bring the minimum to you. Do we have any problem with this sentence? Every vendor want to bring the minimum to you. Some good vendors they want to bring only ESD at the inlet and a typical pressure control valve here, there, خلاص, finish. Take the equipment, please give us our money and goodbye. On the other hand, you can force the vendor to respect your philosophy. How, Muhammad? By giving him your isolation philosophy, asking him, please, I want a positive isolation for all your inlet and outlet connection to the skid. The good question is, where is the skid boundary limit? Here we are. This pipeline, this line. So it is a must for him to be qualified to take the material requisition from my side as an EPC, and he can provide the separator for me. He should provide a skid, simply a skid, as we drawing here, this line. Provide all the inlet or outlet to have the positive isolation. That's my philosophy when I was on the feed stage. He should follow this one. So that's why if you see the older revision of this B&ID, you will see that there is no valve with a spectacle here or there or there or there or in any place. That's the force we give it or we push on the vendor. Please, if you're going to provide us with the separator, we need these technical queries. We need this positive isolation. Why we are interested in positive isolation, Muhammad? To make sure that all the plant have the same isolation philosophy. In case each unit, each skid on the plant will have the same configuration. If we go to another B&ID, for example, you'll see here is a valve on the boundary limit, and I just want to make sure that because there's a compressor, let's go for another one. Here is the package limit, here is a valve, here is a valve, here is a valve. You got my point, Muhammad? Here is the outlet. That's why we are always keeping the same philosophy for each equipment. Muhammad, you follow or no?
Yes, doctor. Yeah. Thank you very much. So, in
Is
terms of maintenance for the separator, I should close all the positive isolation valves that is within the boundary of the separator.
yes, this can be
Okay.
client requirement, or some clients telling you that it is a small plant. So in case of emergency, in case of maintenance, I will just close the well, which is the source for the hydrocarbon, and I will just isolate all the plant. This is the way of thinking also. The way of thinking depends from client to client. If you make this unit for shell, they will refuse to have a valve with a spade, like what we did. If you working for a shell, they will ask you to have a double block and bleed at each boundary limit. So you have to make another valve here with a blade. You have to make another valve here with a blade. The same here, the same here. That's how it's work. Depend on the client specs. If you're working with Aramco, they can accept this valve with a spectacle. You got my point?
Yes, thank you, doctor. Thank you very much.
The other part is the drain philosophy. How we are going to drain this separator. What kind of drain we are expecting, Muhammad? Naja, what kind of drain we are expecting?
Condensate and water.
Totally right. That's why we have open drain and the closed drain. If we have some condensate, it should go to the closed drain. If we have rainwater, we have a cleaning water, it will go to the drip pan, and from the drip pan, it go down to the open drain header. From here, you follow my mouse till it reaches the open drain header. This is the open drain, this is the closed drain. So in my philosophy, if you read it, you can see that I classify two draining system. One closed drain system for the hydrocarbon, it is all over the plant, and the other is open drain system, which is coming from the water drain or the rain water all over the skid. And here's the drain pan, so I can take the water from the cleaning process or the water from the rain to the drain header. This is the second philosophy, which is the drainage philosophy. Relieving philosophy. How I can make relieving happen. Muhammad, take care, because this is the one coming on the causal effect. Same for you, Nash.
Yes, doctor.
How I going to determine the inventory to be relieved? How I am going to do this? How I'm making the relieving philosophy? My relieving philosophy, if you read it, it will come from one, to make some sections for the plan. The sectionalization which we are speaking about last time. I want to define a proper section before calculating the volume of this section, before venting this section. So to define a proper section, you should depend on ESD valves, not on manual or control valves. Only ESD valve for sections. We only depend on ESD valve. So what I did is I put ESD at the beginning I put ESD at the gas line. I put ESD at the surge drum. I put ESD here. Now I determine or select the section I want to be vented or relieved. Based on what? Based on where I insert my ESD valve. 1 here, 2 here, 3 here, 4 here. Based on that, as you can see on the next time, I calculated the volume of this separator, adding the volume of the piping here and there and there and there. Then I sized the pressure safety valve and sized the blow down valve. You got my point, Muhammad?
Yes, doctor.
But there's one mistake. What is the mistake? The cases which I sized the pressure safety valve on and the selection size for the blow down valve. Based on what? Which case we are speaking about? What do you mean? Which case? Let's make a small hazard, Muhammad. What happened if your operator coming to this valve and by mistake, by his leg, he closes valve? What will happen? Tell me.
Yeah, so the discharge line for the gas will be closed, which means that the all gas inside the separator will be kept. So we're expecting an increase in the pressure. So in this case, should the safety valve should be worked, because if it reaches to its design pressure, yeah, this is what I'm expecting. But the problem that we can't depend on PSV as only, because we need to discharge the amount of the gas just like seized here in a quick time, just like maybe the PSV will not help alone to discharge all the gas. So I'm expecting that we need to use the blow down valve as well, just to get rid of all the amount of the gas in here.
No. I'll make it harder for you.
Yes.
Pressure safety valve should be sized to accommodate or to take all the inventory. If it didn't take all the inventory, that means you're making a wrong sizing. Okay?
Yeah, yes, doctor.
This is the first one. The second one, blow down valve, this one is only in fire case. In fire case. Let me share the white screen and let's draw something. Did you all see my white screen?
Yes.
Okay. The way of thinking. Here is the pressure. Here is the separator. Here is the inlet, outlet for the liquid on both sides. What I am trying to do is to define this inventory. Make this happen. I insert a pressure safety valve here, or sorry, ESD valve here, ESD valve here, same here, same here. So I have 1, 2, 3, 4. This is what we speak about is the relieving philosophy. That's why in a relieving philosophy you can see that he will say that we divided this plant to like 10 sections, and from this 10 section we have 10 glue down valves plus 10 pressure safety valves, and keep going all this way. That's the philosophy of relieving. That's all? No. After that, I insert here. We have two cases, Muhammad. Same for you, Naj. One case is called fire case. What happens if we have a fire here? As we said last time, temperature will increase, increasing the level of liquid here, starting to boil off, making some bubbles, making high pressure. Should we wait all this cycle? No. That's why in fire case we have glue down valve, which is a typical ESD, the same ESD as this and this, not a big issue, the same configuration, same everything. What it should do should, in case of fire detector activated, then it will activate this glue down valve. So the first cause and the effect we should make is saying that in case of fire we're going to activate interlock 1, which will close the lock 1. This is the one. Let's write ESD's name or tags. 1, 2, 3, 4, 5. Here is number 5. What I will do in case of fire detector activate, please activate interlock 1, please activate ESD 1, 2, 3, 4, 5. That's how you're going to see it on the cause and effect. That's mean for 1 to be fail, close, fail, close, fail, close, fail, close. So all the inlet and the outlet I closed, and the volume of the gas, the volume of the hydrocarbon inside here will go from this way to the flare by the fail open, which will be the ESD number 5. This is the case of fire. But there's another cases, a lot of cases, like here, as I told Muhammad, this is a manual valve on the boundary limit. What happens if your operator closes it by mistake? So this valve is open, running, and separator is running normally and smoothly. One of your operator close this valve by mistake. What you should do? Your system should defend itself. First of all, the pressure will start to increase. Let me say the what's called the operation and maintenance philosophy, then we'll go for this one. Okay, Muhammad? Okay, Naja? Just I want to take it from down to up, not
Yes,
from
sir.
up to down. Then we have typically pressure safety valve, sized according to API 521. Which cases? We have 26 cases. You have to run it through HYSYS to tell you which volume is the biggest and size on the worst case. That's typical for a three-phase separator. Is the pressure safety valve part of the cause and effect? No. Is the blue down part of the cause and effect? Yes. Why? Pressure safety valve is totally mechanical. No system interference. If the pressure increase, this pressure safety valve will open, and I do not care about anything. The pressure safety valve will say, just give me a pressure, my spring will squeeze and I will release all the gas. Blue down valve is totally opposite. If, for example, by number of this pressure safety valve is sized for 1360 and the pressure inside the separator is almost 1300, this blue down will not respond. This pressure safety valve will not respond until it reaches 1360. This pressure safety valve will start to relieve the gases, and also pressure blue down valve will still the same, not opening. That's I want to clarify that the only case that blue down valve will open is in case of fire. In case of fire. Is that clear for everyone?
Yes, doctor. Thank you.
Let's make it harder. You see my white screen, right?
Yes, doctor.
Okay, let's make it a little bit. Here is the three-phase separator. What we want to make? We want to make the operation and control philosophy. Here is the inlet line. Here is the outline. The good question is, this separator is going to have the pressure inside it equal to the well pipeline, or the pressure will be controlled by before. What does this mean? There is one well here, right? This is the well which is coming in the hydrocarbon. It pumps the gas all the way till it reaches the three-phase separator. The question is, should we install the control valve here or there? Pressure control valve. Pressure control valve. Should I install it here or should I install it here? Was taking the signal from the separator. Muhammad, tell me what your opinion. Should you use one or two? And why?
It should be one, just to ensure that the pressure will comes inside the separator will be within the acceptable limit or is design intent. Because if it is exceeded, so the control valve will just like close, or if it is low, so it will be opened, so it will control the pressure inside the valve, while the number two will not be able to just like do such things. It will just like control the gas, while the one control the hydrocarbon in total pressure.
Okay. Naja?
I think the pressure control valve should be on the vessel. If you have pressure control valve inlet, only it will control seeing the pressure only inlet flow, this one. It may not look into other conditions of the vessel, suppose for fire case or something else with the vessel. So if it is on the vessel PCB, I think it can control all the cases.
Which mean you will choose one or two?
Two.
Okay. The good part of one is it will not allow, in case of high pressure coming here, it will not allow the separator pressure to increase. It will make the pressure inside separator almost constant. Is this one way of thinking? Yes. On the other hand, choosing two is also good. Why? Because what I am interested in, if we have the hydrocarbon coming from the well, I don't want to make any back pressure for the well stream, the hydrocarbon. I just want all the gas to push the hydrocarbon all the way from the pipeline till it reach the separator. Then I can control the gas pressure to go to the separator, to go to the compressor, sorry. This can work if I have a fixed pressure from the well, or if I have a compressor on the downstream, or the well productivity is low. This is a way of thinking. The good and bad part. What we should select. Which one we should select. Naja, if we didn't have a compressor at the downstream, I will select this one, number 2. But as long as there's a compressor here at the downstream, or in another word, here's the separator, here's the gas, here's the compressor. If I put a pressure control valve here and gas is going to the separator, will have another control valve here. This will make a contradictory, which means this one will ask for more gas. This one will control the pressure here. If this one asks for more gas and this pressure safety valve controlling the separator pressure have, for example, low pressure inside the separator, it will close. So this valve asking for more gas, this valve want to reduce the amount of gas out of the separator to keep the pressure of the separator. That's why they are contradicting each other, and that will lead to compressor shut down many times. You got my point, Naja?
Okay. Suppose I can manage with the set points of the controllers. Suppose I can keep the vent valve, the first one, suppose 25, and the second one compressor suction 20. So that as long as 20, this is okay. Only 25 comes, then only first one will activate. I can manage with set points.
Totally right, but this will require a lot of cascaded control loops.
Yeah. Sometimes they maintain this philosophy, like compressor running normally with this the sample suction valve open condition. In case of compressor trip, the upstream valve will a higher set point or ramp they provide, and they open it to vent, so that once the compressor is shut off, the blowdown takes place upstream of compressor. So this is also one kind of philosophy they follow. I've seen that.
Thank you. It's depend on the philosophy, how you are going to control it.
Okay.
Let me give you an example here. I have a compressor. If I put this control valve at downstream of the separator, it will cost me to bring a cascade control loop for the compressor. On the other side, if I put it here, so the separator pressure will be controlled by the compressor suction pressure. So no need for any other cascaded control. It will be like feed forward control loop, normally one. You got my point?
Yeah, this is one kind of control. Yes.
Okay, Muhammad, you lost, right?
Okay, yes, doctor, a little bit.
Okay, what we was speaking, me and Naja, was like, if we select position number 2, we will end it up by, we have, let me make a new one, because it is a good one. We will end it up by, have a separator, have the pressure control valve, taking the signal from the separator, then going all the pipeline. Then I have a pressure control valve for the compressor. You got it, Muhammad? You see it?
Yes, doctor.
This pressure control valve, and this is a pressure control valve. This function is to keep constant pressure to the compressor, and this function is to keep also constant pressure for the separator. The question is, or the problem happened when this pressure control valve asks for more gas. It will start to open more, like 70-80%, to allow this compressor suck more gas from the pipeline and from the separator. This one. On the other hand, when this compressor making like this pressure control valve will start to feel that the pressure inside the separator is going down. So this pressure control valve will start to close, cutting the feed to the compressor. Based on that, the compressor will go to the surge and start to recycle some of the gas, which we don't want to do this. That's why we have a contradicting opposite direction. This valve is closing and this valve is opening, asking for more gas. That's what we receive. What happened when you put two control valves on the same pipeline. So as a rule of thumb, if you work with if you work with instrumentation people, good instrumentation people, they're always telling you that do not put two control valves on the same pipeline. But there is a lot of control valve on the same pipeline. The rule is, let me put it here, write it here, do not put two control valves on the same pipeline controlling the same variable. What does mean, Muhammad? Here on the bottom we was controlling the pressure inside the separator, and this pressure control valve for the compressor is also controlling the pressure. So what we are trying to do is, what is prohibited for us to do is, do not put this two controlling variables on the same pipeline. This is controlling pressure and this is controlling pressure. So do not do this because it will cost you money. I don't get it. What we should do, let me make another one. Here is the separator, here is the pipeline, here is the control valve for the compressor, and here is the inlet. Right, Muhammad?
Yes, doctor.
Okay. Here is the compressor, here is the separator, here is the pressure control valve at the inlet. This pressure control valve at the inlet supposed to take the signal from the separator, sensing on a normal operation day, if the pressure inside the separator start to reduce, this pressure control valve will start to open, sending more hydrocarbon from the well to the separator. On the other hand, this one, in a normal operation day, if the pressure here start to reduce, this pressure control valve opening to send more hydrocarbon to the compressor. So, if the compressor wants more gas, this control valve will open. Pressure in this pipeline will start to reduce. So the pressure here, its separator will start to reduce. So this pressure control valve will sense that the pressure is reducing, so it will open more to send more hydrocarbon to the separator. So this valve open, this valve open, this valve close, this valve close. Why? When this valve close, that means there is a high suction pressure, a high gas. So this valve will start to close a little bit. Instead of 50% opening, it will be 40% open. So the pressure will increase. The pressure inside the separator will start to increase. So this control valve will close. So this valve open, this valve open, this valve close, this valve close. This is called linear relation. Linear relations between the control valve is the easiest for the instrument engineers and for controlling purpose. That's why all designers all love to go to this site. Is it clear, Naja?
Yeah, I understood, doctor. Now I understood. So earlier, what I'm saying, suction pressure controller, actually, how they do is with RPM. In case of pressure coming down, they will not do any pressure control as such, but that PT indication they give it to RPM, and RPM will reduce or increase base to maintain the pressure. So it's not pressure control what I am telling right before. Yeah, you're right.
Okay, there is some good compressors coming with no pressure control valve here. They depending here on three variables: RPM and recycle and suction pressure reading. Suction pressure reduce, you start reducing your RPM. Hamad, what we are speaking about is how your normal centrifugal reciprocating compressor work. Hamad?
Yes, doctor. Yes, thank you.
Yes, this is the RPM, this is the recycle, this is the suction pressure. If I am the operator of this compressor, I have to know this. What is controlling your car is your RPM, which is gasoline you bought in your car or how much you press. Then we have the recycle, which is in your car that you don't have. And the suction pressure, which is in your car, is the wind direction. What we are trying to say in another words, in an oil and gas words, that your suction pressure is reduced. Normally the compressor will start to reduce the RPM, so he will start to suck more low gas from the pipeline. But if the suction pressure reduce more, then the recycle valve will start to open, taking from the discharge back to the suction by the control valve here, which is automatic process, which is called the surge process. For the recycling, this is the two ways of controlling Muhammad. But what happens if the suction pressure increase? The
Yes,
machine,
doctor. So this is specifically to reciprocating compressors?
Yes.
Sorry.
Yes, totally right.
Okay, thank you.
It is a general for any compressor, but keep it now for a reciprocating compressor. For centrifugal, yes, reciprocating compressor, sorry. What we are trying to say, what happens if your suction pressure increase, automatically the RPM for the compressor increase to allow to make more power to suck all this additional gases from the pipeline here. Did you get my point?
Yes, doctor. Thank you. So
Naja,
in this case,
yeah.
still the second control valve will be needed even when the reciprocating has just like this recycle valve,
No,
or we don't need it.
I
Okay,
don't want
okay,
this one. I will depend on the
okay.
compressor
Thank you.
suction capabilities.
Okay, yeah. Thank
He
you.
feels the suction low, he will start to reduce the RPM. He feels the suction is high, he will increase the RPM and keep going. Let's go back to the cause and effect. We didn't do the cause and effect at the moment. Now I am your operator and I have the separator here. What we are going to speak now is the first layer, which is the operator. Then we'll go for the safety instrumentation system for the phase separator, 3-phase separator. From the B&ID, we know that there is a pressure control valve here and another one here, level control valve, and another one here, right? What we are trying to do or trying to control is the pressure, the temperature, the quantity, the level. And typically in a 3-phase separator, temperature don't have any control. What happened? Sorry. And a 3-phase separator, typically the temperature don't have any control. We need to control the pressure, we need to control the flow, which can be controlled by if you control the pressure. So you will control your pressure, you control your level, pressure of the gas and the level of the liquid. So we have this pressure control valve. It is taking the sensing from the pressure transmitter, which sends the temperature to, sending the pressure to the control room, and from the control room we have the setting for this pressure control valve and we make it open or close according to the setting. This is a typical control loop. Something to feel, something to measure, reading sent to the control room, where the operator will put the set point and the computer of the DCS will start to compare between the set point of the control room or on the set point which is the operator bought it, and the reading coming from the site, which in this case called a process variable. And he brings the difference between the set point and the process variable, and he make a correction, or he simply making equations and bring the error, which is the difference between the set point and the process variable, then sending this error to the pressure control valve or the control valve, asking the control valve to open or to close. This is a typical control loop. Is it clear for everyone, or should I do it in more easiest way?
Doctor, just wanted to ask you about the set point. How can it is specified? Is there any criteria to specify the, for example, in this case, the pressure, set point pressure?
The tripping and setting alarm you received from your EPC contractor. I will tell you how to make it.
Okay.
Don't worry. Just
Okay, thank you.
I want to make sure that you are understanding the basic control loop, how it's works.
Okay, yeah.
Do you have
Yeah,
do you
so
have
it just-
do you have a bottle of
since-
water in front of
since-
you, Muhammad?
Sorry?
Do you have a bottle of water in front of you?
Bottle of water?
Yes.
Yeah.
Touch it. Tell me it's cold or hot.
Swarm.
It's warm. How you know it's warm?
By touching it.
What happened when you touching the bottle?
Yeah, they're just like this, just like his skin or nerves will just like send a signal to the brain. So,
Yes, totally right. It is the same. That is the origin of the control loops. Here is
Yes.
your nervous system on your hand. Here is the nerve in your hand, feeling the temperature. Then by electrical signals inside your nervous system, it go to your brain. In this case, the brain is the control room, where in your brain there is a set points by the gut telling you that it's too hot, so the brain will send automatic another electrical signal to the muscle in your hand, which in this case is the pressure control valve, to take the action, leave the bottle, or here open or close. You got my point? It is a typical what we
Yes,
have in
sir.
our normal life. This is the origin of the control loops, by the way. Something to sense whatever you want to sense: level, quantity, temperature, pressure. This is the most critical 4 variables in any process. Something you want to sense, which is coming from the PT, TT, quantity flow meters, or level transmitter, whatever. Whatever sensing, then sending the reading to what? To the brain, which in our case the control loop. And from the control loop, there is in our brain, if you see a small child and he put his hand on a hot oven inside the kitchen, by default, and no one want to tell him remove your hand, he remove his hand. Right?
Yes, yes, doctor.
For a small child, this is called the trip. The trip. What's meaning the trip? The muscle or the control valve take an action to close. But if the small child or you, Muhammad, can hold the bottle, and the bottle is not that warm, so it is operating. I don't get it. Let's give you a good example. For here, for example, here is the weir inside. The level of water will be like this. All this, let me make it in blue. All this will be water. All this will be condensate. Normally, Here we want to control the level through this level control valve. So what we want to do is to have something to read the level, which can be a displacer, radar type, or level, even normal level glass. And from here we need to send it to the brain, which is the control room, and from the control room will be the set point. What is the set point? What's coming from the vendor, or on another word, Muhammad, the level of liquid here, which is, in this case, let's give numbers, or let me say it in another word. Here is the separator, Muhammad. Here is the bottom of vessel. We have normally four triggers: the low and the high, the high, and the low. It can go for the level, can go for the quantity, can go for the temperature, it can go to the pressure, depending on what you want. Let's give for the level control valve. From high to low, this is the part where your operator have the right to work. For example, by number, let's give some numbers to make it sensible. Low is on 300 millimeter. Low is on like 600 millimeter. High is on like 1-2 millimeter, and high is 115 millimeter. What does this mean, Muhammad? As long as the level is 600 till it reach 1200, the control is given by the level control valve. As long as liquid increased reaching 1000, this sensing element giving signal to the brain, where the brain try to make a comparison between the set point and the what's the reading. For example, if this 1200 and our set point, like let's put it like 800 is almost 50% between the low and the high. That's what we are trying to keep. For example, now if the reading is coming like 1200, what, this is the process variable, this is the set point. So what the brain will do, Muhammad, he will calculate the error equal PV minus set point, or in another word, set point minus PV, depend on the signal. So 1200 minus 800 will have 400, which is a big gap. So this 400 will be transmitted in electrical numbering, in electrical signals, to the level control valve, to the solenoid of the level control valve, where it will allow air to enter to the control valve to, we have 1200 for the high. Now it is, let's make it 1100, so keep it below, inside our limits. You will understand why now after 5 minutes. Now we have 300 gap, this 300 will be transmitted by electrical signal to the solenoid, where air is being introduced in instrument air to the control valve, asking the control valve to please open more to drain this liquid, to get off this extra liquid and keep the level inside here at the 800 level. On the other hand, if the process variable coming like 650 millimeter coming from the level transmitter to the brain, and then making the comparison, 650 minus 800 equal negative 150. Negative 150 will be transmitted by electricity to the solenoid, and from the solenoid it will introduce some air, or remove some air in this case, to allow the spring of the control valve to take the action and close a little bit to build up some liquid inside the separator. This is coming under the controlling and operation philosophy of the separator. As long as we are between the level of low and high. Is there any question in this point? Should I go forward?
Yes, sir, please. Thank you.
Naja?
Yeah, very clear.
Okay. The question now for the cause and effect. What will happen if when this level transmitter measure 1200 or measure 600, which is the high and the low. The question on another word, what would be the consequence if we have more liquid here? Muhammad, what will be the consequence if we have more liquid, more than the maximum?
Well, just like exactly, doctor.
Here on this compartment.
Yeah, this is the problem, that there is a delay, so I can't follow your mouse. So, which part? The water section, the condensate, which one?
Condensate section, if we have a more condensate on the condensate section, high level, what we are afraid of.
Yes. We are afraid that it will be mixed with the gas, so it go to flare, make just like black smoke, which affect the environment, I think.
Totally right.
So
we are afraid from the carryover. Carryover is just the liquid will go with the gas to whatever go. If it is go to a compressor, it will damage the compressor. If it is going to the network of distribution, that means when you open your oven, you will find liquid coming with, which is not acceptable. So, in case of high, we are afraid from the carryover. So, in this case, we have, one, we are afraid of high for the level. We want to stop this from happening. This one. 2, low level, What happens if we have level below 600 nausea?
If it goes to pump section, it will cavitate.
It is not going to a pump section.
If there is a low level, gases may escape into liquid from top.
Yes.
Vapor space.
Totally right. That's what's going gas flow by, and here liquid carry over. You got it? One, liquid, we are afraid from the liquid carry over. We are afraid from the gas blow by if we have low level. High level, high level, liquid carry over. Low level, gas blow by. Is it clear for everyone?
Yes, doctor, thank you.
Okay, this will come in the cause and effect. We have the first one, high liquid, low liquid, low level, high level. This is for the level. The good question is, let me share the BNID again and ask you. Muhammad, in case of liquid are increasing here, what we should do?
There is just like a control valve which control the level, so it will send just like from the sensor, it will send the signal that it is reach high level, so the control valve will just like try to open more to discharge the excess amount of liquid.
What happened if the control valve didn't respond?
Didn't respond, So the level will be increased until it reach the high level, which an alarm will be sent to the operator to just like do intervention.
No. Let me stop you on this one.
Okay.
From low level to high level, operator has the right to intervene. From high till it reaches a high, the operator has the right to intervene. Once it reaches a high, operator don't have any right. It don't have the right to intervene. System will take care about it.
Yes.
That's why we make the cause and effect. The question for you: if we want this system to close safe, or in another word, to fail safe, and the level is increasing unlike this part, at this part the level is going to increase, what should we do to prevent the carryover from the liquid here with the gas line, as you said before?
Maybe I'm thinking about just like the no, it's the same. So to prevent. What about the other part? I mean, the water part can be helped, just like if we discharge and increase the flow rate of the discharge.
No, you cannot discharge hydrocarbon with the water line.
Uh,
Mm,
there are a couple of options.
Tell me, Najib.
Okay. One thing is we are seeing one more level transmitter. So in case of high level, that can also open. It will be given further high set point. You can see left side one more level control valve.
Ah,
This is one
I don't
thing.
get it.
You
I am-
can see the LT3004. One more oil, water.
Let me
Yeah.
just let me.
So this is also controlling the level.
Is this one?
This is what we are controlling now.
Yes.
Uh,
You speak about
and
this
I'm
one?
saying left 3004, yeah.
What about it?
So this is also controlling some level in the vessel.
Yes, but it's controlling, but it's not my question. My question, what we should do if this level transmitter measuring liquid condensate, and one time during normal operation it's give a high alarm. After like 10 minutes this level switch is the high is start to activate, saying please I am in trouble, liquid is carrying over, liquid is above my limits, and liquid is going to increase high. So it will go, the liquid will go with the gas. It will destroy all the downstream equipment. Please,
Okay.
you need to prevent this from happening. How
Okay.
we can prevent this from happening?
So one thing is that high alarm giving to DCS operator so that take action by operator action.
No.
Our second is automatic high is interlinked to ESD shutdown system.
Naja, high alarm, operator. High operator don't have any control.
Yeah. Okay, then
Yeah.
high lead to ESD trip. Yeah.
So, Doctor, I think the interlock will take action. So, just like stop feeding the separator.
Yes, that's what I am trying to understand. Or trying to build the causal effect. Which action we should take? This interlock, which valves should actuate, should activate to prevent the carryover from happening? Should we close the inlet? Should we open the pressure safety, the blow down valve? Should we open the liquid level? Should we close the gas outlet or open it? Let's make one zoom out here and ask. You insert a flow control ESD valve, shutdown valve 4404 here at the outlet. The question is, if there is more liquid coming up here, you want to add more hydrocarbon to it, or you just want to stop the feed?
Stop the feed.
So the first one, this high will make interlock, and the first valve to put in this interlock is one shutdown valve 4004 will close. That's one. What else? What else? Should we close this one or open it?
Should be closed to avoid the carryover.
Thank you. This is the second valve to insert. Here, for the shutdown for the liquid side, for the water side, should it open or close?
Just this will be closed according to it's just like a trip set situation,
Why?
because it is failed closed.
I don't want to ask for filling close. I'm asking what happened if this high trip activated. Should it close this one? Should the interlock close the shutdown valve? Yes or no?
No.
Why?
Why? Because whatever the level we need to drain, you have to make sure that this level comes to normal operation. So this should not get closed. It should not act, interlock should not act on these walls.
What's your opinion, Muhammad?
Yeah, I totally agree that we need to close the gas to prevent the carryover and to open the discharge for the liquid and the water line to return back the level to its original state or acceptable state. But what I didn't understand that because we already the shutdown valve sent a signal to the interlock just to take action. So the action in both these lines is closed. This is what I didn't understand. So if you can please explain. Thank you.
No. The action is to open or to close. This action we are searching for. What is being right here on the B and ID is the failing position. What happens if the utility instrument air is failed? This is the action this valve will take. That's why if you are making the drawing by your hand, you will notice this small numbers, small ticks. You got my point, Muhammad? That's why it was interesting to make it by your hand.
So this FC fail. So FC fail close. It means when the
instrument
valve
air
is not working or the whole system.
When the driver for the valve, which makes the valve open or close, which is the air, is not there, this valve, the spring position, will force this valve to close. Force this valve to close. Force the blue down to open.
Yes. So, and just like if there is any problem with the valve itself or the supplying of air, so any of these cases, this will fail, right?
Totally.
Or
right.
just in case of there is no. Okay. Okay. Thank you.
The question
so
the question is, in case of this trip happen, and we are on the stage of building our cause and effect, this high is activated because the operator was on the launch break and he didn't notice the screens. Now the high is activated. We are developing the cause and effect. We said that this valve should be closed. We said that this valve should be closed to prevent the carryover. This to reduce the level inside the separator, and you go to this valve and you tell me that we should open it to drain the liquid. The good question is for both of you, what happened if we didn't know which liquid is inside? Is it water or is it hydrocarbon? If we didn't close this one, this means that all the liquid here, all the liquid inside the separator will simply go to the evaporation bond, which may be hydrocarbon and water. In this case, we will end up by have another problem at the evaporation bond, where all the liquids are being transferred. Right?
Yes, but we can solve this problem.
Yes, but we also can solve this problem high here.
No, I mean when discharged for both the liquid or the water line, this should go to the just like the drain system, closed drain system, because we are not quite sure if it is totally water or hydrocarbon with it, until we just like reach to the acceptable level, and then we can return back the the just like the each stream to its original state according to the just like tests will be done.
What you just say is totally right. If your philosophy is what you say, you got my point? If your philosophy
Yes,
of
doctor.
drainage is like what you say, this will be totally right. But if my philosophy as I design it, I will close this. Why? And keep this closed also for the high. Why? It is almost condensate, and you know it is condensate. You will close the outlet of the condensate? Yes. What I preferred, what I learned from Shell, what I love from Shell actually is, if you have a problem in one of the inside of one of your equipment, the first thing you love to do is to isolate your equipment. Isolate your equipment. So, and the cause and effect, when we go to the cause and effect, you'll see that if we have a high here, I will close this valve, follow my mouse, I will close the outlet valve, inlet valve, the liquid valve for the condensate, and also for the water. Why? Why you are doing that? You have a high level of condensate inside there. I will do this, and so this equipment will fail safe. Now I am sure that this equipment didn't have any problem inside the high. I will start to operate on a manual mode. What's mean of manual mode? That's what you said, Muhammad. Take care about this. Look, I will open this manual valve all the way down till it reaches the closed drain header, because I know it is what? It is a condensate. It is a hydrocarbon. So all the way from here, sorry, follow my mouse please. From here, go down all the way till it reaches the closed drain header, will be filled with the hydrocarbon which I am suffering from high level. You got my point, Muhammad?
I'm a little bit confused because you said we need to close the discharge valve, but at the same time you said that we need to open the one. So just a little bit, can you just please repeat it quickly, if to just like to get your point, please?
We close the shutdown valve, right? This one.
Yes. So this is manually.
No,
so I will just like take it.
This shutdown valve will be on the interlock. Here is the I interlock signal. It will close automatically. I don't have any problem.
Sorry, doctor. We said that at the beginning that it will be open, right?
Which beginning? Which situation?
I mean, let's just take the scenario again. Okay. Now we have high, okay?
Yes.
So the shutdown sent to the interlock at the beginning of the inlet of the separator to close it, okay?
The first one. Huh.
Okay. Now move to the
gas suction. Gas. Take the gas off.
Section and close it as well.
Okay, perfect. The liquid section.
Now we have the condensate and water one.
Yes,
so
we
this
will
will
close
be
both of them.
As well.
Yes. So you are isolating all the separator. You isolate all the separator which you have a problem inside it.
Yeah, and open the drain system for both the condensate and water.
No, for the condensate only at this point, because we have a high.
Okay.
This is a type of operation. I love it because it is very safe. How I can say it is very safe? Because I isolate all the section. isolating all the section, making sure that this equipment will be failing safe depending on the system, not depending on the operator. But on other philosophies, on other clients, not Shell, like Aramco for example, they don't love to isolate all the equipment. As I said, they try to leave it, or simply they try to, as you said Muhammad, to take all the liquid to the evaporation pond, and from the evaporation pond they can manage to recover all the oil from the surface of the water. Is this another solution? Yes. It is acceptable by Aramco? Yes. It is rejected by Shell? Yes. This difference between the clients. Both are right, both are operational, both are maintainable. I don't have any problem with both. The good part is that you have to follow the philosophy you have developed on the field. Here, I developed the same philosophy as at Shell, which I will close all the vessel, I will isolate the section. After that, I will start to handle the problem. This is the Shell way. Isolate, then start to handle. That's what I did. I isolated all the shutdown valves. I isolated. Then I start to handle by draining to the closed drain if it is condensate. If it is water, I will go to the open drain header. Both are workable for me. That I was trying to do. That's for high. Let's take low Muhammad. Or Naja. You are the one for the low. Naja? Is she with us?
Yes.
Yes, I miss your voice.
Okay.
Okay. Tell me. Faiz is with us and he didn't say a word. Faiz.
Yes, go ahead, please.
I miss your voice last time.
Thank you very much. No, I'm listening.
Are you
the
following
discussion.
us?
Yes, I'm following very carefully.
Okay. Now we have the low activated. Which valve we should close, Naja? Tell me.
If low level is activated, you're asking about these two valves, which one to be closed?
Yes.
If the low level is activated, then definitely the bottom one has to be closed.
Okay. Let's start from the inlet. Should we close this one?
This one should be left open, and the gas one is left open. The water and condensate should be closed.
What about your opinion, Naja? I love this because this is the discussion which will make a mark in your brain.
Yes, totally.
What's your opinion, Naja? Should we open or close this one?
The inlet valve?
Should we open or close the inlet valve?
Inlet valve, inlet valve to the low level.
Yes.
Low level, yeah, it should be open. No issues if it's open.
It depends.
People.
It depends what you want to try to do. If we make a HAZOP and a cell assessment after this, we will see how much risk we are introducing to the system by keeping this open or closed. Till the moment, I don't know. I want to understand why we should open it and why we should close it. When to open it and when to keep it closed. On the cause and effect. Muhammad, Naja,
Yes, doctor.
Faiz, anyone reply to me.
Yes, doctor.
Yes, tell me, should we keep it open or closed? You said keep it open. What happens if we close it?
If we close it, so we will expect that we will not just, we are trying to increase the level. So in this case, the feed will be stopped. So we can't in this case. So we need to ensure that this will still open just to provide the required level to still going inside. And as I said, we need to leave the gas one, which is 4008, open, okay, to give space to the liquid to increase, so any volume or space has been occupied by the gas will be discharged. And keep the 4008 the condensate and the 7 in the evaporation pond closed. So there will be no discharge for both liquid and water. So we increase the level inside.
Simply, what you're saying is you trying to close all the liquid outlet to build up the liquid inside the separator, right?
Yes.
Did I understand it right?
Yeah.
Okay. It is a good philosophy. Naja,
Thank you.
are you agree?
So yeah, it depends upon the philosophy. Suppose the owner interested in keep not shutting down the complete system, then this is okay. So if level is there, you can maintain and you can attain this level or control problem or whatever. You can build up the level. This is one thinking. Or if there is a low level has come, I want to completely shut down. Yeah, it depends.
Sorry. Doctor, I think just like I have a comment just like in terms of gas. So just to ensure if there is a compressor that there is no more gas just like required will go there. So it will know maybe the control valve will close as when the section pressure of the compressor will be just like as it's required set. So I think in this case the PSV will be open. I think if there is an increase or just like in the gas, this is what just like as a comment I wanted to understand if this is the scenario will happen or not.
I am loving because this discussion is more fruitful. I love it. Let's take it from bottom to the top. The question is, if we have low level here on the condensate compartment, on this section, here is the weir, adjustable weir. So that means this part is condensate, this part is the water. The question is, if we have low here, which is achievable, achieved or activated for any reason, we don't want to give the response to the operator. Based on that, we want to make the cause and effect to make sure that this equipment will continue working safely. What we are afraid from the low is the gas blue by. which means gas will level here will reach 0. Then gas will go to all the way to the surge drum. We want to stop this. Why? Why you want to stop this? Because what we shown said to the surge drum is only condensate. The condensate surge drum is running at 200 psi, and this separator can run at 900 psi. So in this case, this 900 psi gas, if it's go to the surge drum, it will explode the surge drum. It will totally increasing the pressure of the surge drum, and if we didn't put the correct measures, it will explode the surge drum. So what we are trying to do to prevent this from happening, how we can do it? By inserting a shutdown valve here, which is 8. Should we close it in case of low? Yes, this is what we are trying to do. This for the shutdown valve. On the other hand, for the gases, for the liquid one, first thing we will close 4008, we will close this shutdown valve. Interlock will go to close it. What else? If we have low level here on this part, and here is the weir, this means maybe we have also another low level here. So if this shutdown valve 4008 closed for the interlock, we also, for security reasons, to make sure that we don't have gas coming all this way going to the evaporation bowl, we also shut down 4007. That means 4007 and 4008 are closed to prevent all the liquid from getting out of the separator until there is a proper level inside the separator. Does anyone have a problem?
No, thank you.
This means when the interlock is activated due to the low, we will close these two valves. The question is, should we close the inlet? Should we close the outlet and make a stop or shutdown for the compressor on the other side? If this gas was going to flare, I will close all the inlet and outlet. But this gas is going to the compressor, which is making extra pressure to the gas. So stopping the compressor every time we don't have a level of liquid inside the separator, and rerun it again when the level is increasing inside the separator, is non-relevant, which means that what is the relation between the compressor and the liquid level inside the separator? Liquid level inside the separator, we should prevent it liquid from reaching to the compressor, which will make it by the high. On the other hand, low level don't have any connections with the gas section. If we have a low level here, this means all this section is filled with gas. So why I should close this one or this one in this case? This one or this one in this case? But actually, as Muhammad said, I should keep this open and keep this open to allow for gas in, liquid in, and allow gas out and liquid increase here to go away from the low level, go to the low level, going to the high level. To go to this section of operation. That's why I try. I shouldn't close this one or this one. I should make the path for the gas is open and only close the path of the liquid until the liquid build up. Everyone follow me?
Yes, doctor.
Okay. We will take a break for, let's say, this. What's time now? This is 9:30 at my side.
Yes, 10:30.
Okay, we will take 30 minutes break. Okay.
Excuse me, doctor. Just have a suggestion before we go to the break, please.
Yes, tell me.
I mean, just in case. So, I mean, let me understand this point first. So, the pressure of gas will be towards the water and condensate discharge, or to the gas stream discharge line. So, I mean, according to the pressure applied. So, the flow will be this side or the more at this side, at the bottom or at the top.
Okay. Consider yourself as a gas. You have one side asking you and have a suction pressure. Suction, there is someone absorb, which is in this case the compressor, absorb the gas. He asking there's all be all the way there will be the driving force to the top, not to the bottom. What happens when the liquid level reduce? By default, as the liquid reduce, the gas will fill all this area. Gas will fill all this area to make sure that there is a pressure on the liquid level. So gas will fill this area and stop from going up? No. Gas filling this area, portion of the gas will go to the top, 90%, and 10% of the gas will fill this area to compensate the level of the condensate which was in this part. You got it or no?
Yes, doctor, but I mean in terms of gas blow by, so it just like some of the gas will go within the hydrocarbon stream. I mean,
just imagine that the liquid level here is 0.
Yes.
Just 0. If the liquid
Yes.
level here is 0, that means all this is saturated is gas, right?
Yes. Yeah.
In this case, what will prevent the gas from coming on this line? Follow all this way till it reaches the surge drum. Nothing, right?
Yes.
That's the most critical for us. Why? If gas reach surge drum, it will explode. So what we want to do is to prevent this from happening. So we cut off the way. How we cut off the way? By installing this shutdown valve. Make sure
Excuse
that-
me, doctor.
Yes.
The surge drum, sorry, the surge drum will be exploded due to the increase in the pressure, right?
Yes.
So it will exceed it. Okay. Okay. Yeah.
That's why we bought this pressure safety ESD valve on the way to cut off the way in front of the gas to prevent the
Yes.
blow-by case.
Yes. So in this case, I think it is better to just like install a pipeline from the top of the gas stream, the top of the vessel, the gas stream itself. Okay. So goes to the flare, and we should put a control valve. What do you think? Just to avoid any excess gas will maybe has a negative effect on the compressor.
You want to make another pipeline here, go like this to the flare and put a pressure control valve on stated. Right?
Can I just take the control, please?
Yes.
Yeah. So from this line, let's say, okay, doctor, you see my mouse? Now
Yes,
moving.
yes.
Okay, yeah. So from this point, so make a pipeline goes to the flare, okay, and put a control valve which set point according to the required section pressure of the compressor.
Okay, it's the same.
As we will,
The same as I did it here.
well, yes. So there is one already installed. Oh, okay, yeah, okay. I mean in here because it is not drawn.
Yes, you ask that why we should install a pressure control valve to take off the gas in case of the compressor
The
shutdown,
excess
right?
gas, yeah.
Did you read the basis of the design? Hamad,
Sorry, doctor.
did you read the basis of design?
Yes.
No, you didn't read it.
Why?
Because if you read it, it's just how I can remove the control. I want to make sure that.
So I will stop it.
Okay,
Yeah, okay.
please. Okay, thank you. If you read it,
Sure.
you will see that on the basis of the design, the owner or the owner, the client, asks that in case of compressor shutdown and compressor not working, we to have the ability to bypass all the facility. So in case of the compressor shutdown, one of their operator will have to close this valve to make sure that all the gas from the well is coming here back to the bypass for the total plant bypass as per note 6. Total plant bypass. You get my point?
Yes, doctor. Okay, yeah.
So down here, in case of compressor not working, not sucking all the gas, I shouldn't divert the gas to the flare. I should divert the gas to the bypass. All the facility should be bypassed from here to the Sharabas manifold. You got it?
Yes, doctor. Yes, thank you very much. Thank you.
You're welcome.
Yeah. So, sorry, just like I take from your break time.
No, take your time. Don't have problem.
Thank you.
You're welcome.
Much appreciated. Thank you.
You're welcome.
Okay, see
We
you
will
inshallah.
come back after 25 minutes.
Okay, inshallah, doctor.
Okay.
Lord.
Here we have the high and low for operator to intervene. High to stop the separator in case of overpressure, and low in case of there any break, any something fail, any pipeline rupture downstream of the separator. What will happen? All the gas will release to the atmosphere. So to avoid or to eliminate or to reduce the amount of gas will go, for example, if we have this line break, what will happen? The pressure will reduce. Low alarm. If we didn't have low alarm which close this control valve, this will continue leaking forever, continue rupturing and releasing gas forever until someone close the well itself, and we don't want this. So what we are trying to do is to have a low to protect against any pipeline rupture inside the plant. You got it, Naja?
Perfect.
Okay. Let me share this, then this white screen, then we will
Your
jump.
voice was breaking, please.
I will say it
Can
again,
you please
Muhammad,
just
don't
repeat?
worry. I will say it again. This is from the last day, Muhammad. This is from the last day. Normally, if we have our
Yes,
operator
doctor.
here, our operator simply, if we have a separator, and we will speak about the pressure now, only pressure. Normally, operator have the ability to work between the low pressure and the high pressure alarm. Low pressure alarm is the minimum for the operator, and the high pressure alarm is the maximum for operator. This section called operation intervention. This is the basic process control. Remember this word, basic process control. That is what I am doing in my car. Normally, for example, in my car, I'm using the transmission, the gearbox, the normal brakes for normal stops. But ABS activated in emergency situation. So high pressure trip, low pressure trip, making the tripping or the action zone. On other word, on function safety words, it's called safety instrumentation system. Remember also this word, please. Basic process control, which is the operator has the right to make click on the mouse on the screens to interfere and take action, increasing or opening the valve. Safety and instrumentation system, however, the operator don't have any right. He didn't have any right to do anything. System will take care about the equipment. It's called safety and instrumentation system. In other words, in car language, which I love it, basic process control is the accelerator, the normal brake, and the transmitter. SIS is the EBS for the brakes. Naja, if you are driving and you find something in front of you, something in high speed, you normally push your brake slowly or very hard.
Hard.
EBS need your permission to activate it, or it is activated automatically.
Automatically.
This is the same here. It is the same here. That's why we make a cause and effect. To make sure that all the system automatically safety instrumentation system is running well. So in high and low we activate the interlock I to prevent more gases from entering and prevent any gases from outlet until you correct your position. What does this mean? If I close the inlet valve, let me remove this one. Here is the ESD at the outlet, and here is the ESD at the outlet. Once the pressure has the high, it will activate the interlock, and the interlock will close the ESD at the inlet at the outlet. Now the pressure here is high, so here is the pressure safety valve. I will work on the bypass to open it gradually to venting the extra gas. This should be written in the operation manual, relieving philosophy, and written B in the operation manual. In case of high pressure, this valve will close, this valve will close, as this one activate the high interlock. Then the corrective action you should take is venting the extra gas through the bypass of the pressure safety valve. This is the high. And also for the level, we did the level few minutes ago. The question is, Muhammad, let me choose another color. Here is the basic process control. Here is the safety instrumentation system, and there will be also the flow down valve and pressure safety valve as the fourth one. This blow down is for fire case. This pressure safety valve is for all the 26 cases we're going to take next day. The 26 cases consider fire, blockage outlet, gas blow by, and all of this. This is the pressure safety valve, this is the blow down valve, this is the instrumentation system. Here, this is the basic process control. Here are the 4 layers of protection. 1, 2, 3, 4 layers of protection against high pressure. Do you know that if we are going to HAZOP this separator and we ask for what happen if this basic control fail? The control valve is stuck open, malfunction open, inadvertently closed or open by mistake. We should have our tripping system as a safeguard. You follow me, Muhammad, Naja, Faiz?
Yes, doctor.
Naja? Naja,
Yes, yes.
Faiz,
We, yeah, safety interlock system, a layer protection.
safety and instrumentation system, which
Yeah.
is like in your car the EBS. What we are doing in HAZOP is we challenging this. We challenge this basic process control. We say it is not in place. We say the operator is asleep or doing a mistake. Based on that, we are seeing another 1, 2, 3 layers. For a HAZOP, if you have 2 layers, this will be enough, more than the basic process control, to achieve something called cell 2. I will speak about this next time, inshallah, as a minimum. Okay? Is it okay for everyone?
Yes, doctor, yes.
Here is the cause and effect. How we can read it and where to start. Everyone have in his mobile or in another page or another screen the BNID in front of his, and also I will share this one. I will share the cause and effect on my screen. Try to make the group separator on your other side. Okay. Let me undo all. Here is the separator section. We have pressure alarm high from 3 separator system. PIT 3007. Let me see where is PIT 007. Where is 3007? Here we are. This one. He's speaking about this one now. You follow me? Let's go back to the
Yes, doctor.
3-phase separator. Thank you, Muhammad. He's speaking about the BIT is 3007. If we have high alarm high from the 3-phase separator, it should activate. X mean activate. Let's go up to see what it activates. It should give you audible and visual alarm. Audible mean it may make a noise in the control room. Visual alarm will pop up in front of the operator at the DCS. Audible mean there will be like a siren, something saying take care, they have high pressure, and visual alarm will pop up in front of the screen, in front of the operator, in the middle of the screen in front of the operator. This is the BIT 3007. It is for the high pressure, and also it is for low pressure. It's the same. Here, audible and visual alarm. So 3007 will have nothing except it will make alarm saying please take care, we have emergency situation. Now let's go for a high from the 3-phase separator. Pressure alarm high from three-phase separator, which is BT3006. Let's see 3006. That's one. We speak about this one. We speak about this one. You follow me, Muhammad?
Yes, doctor.
Okay. Let's switching back to the 3 cause and effect. Now we have a high alarm. Will activate X here. Total plant shutdown. Total plant shutdown. Which means closing all the shutdown valves. 1. Continue. Here. It will close shutdown valve number 4004 at 3-phase separator inlet shutdown valve. It will what? Closed. It will closed. Here is our, just I want you don't, here is the same line we are following, so you will not lose. The third X, it will make audible and visual alarm also. Here, if there any, I just go to the end of the chart. Nothing. So our high pressure alarm will have 3 actions. 1, to give you audible alarm. 2nd, to close the inlet of the separator. 3rd, will cause a plant shutdown. This is for high. Do anyone have a comment on it?
No.
Okay. Let's see the low. Here is the low from the 3-phase separator. Then we have the here also total plant shutdown. Here closing the inlet of the 3-phase separator, and here we'll have the audible alarm. It is the same. High is the same as the low. You got it? Faiz, are you with us?
Yes.
You got it?
Yes, familiar with the cause and effect, yes.
Okay, good. Muhammad,
Yes, doctor. Thank you.
okay. That's how we generate it for the pressure. The same for the water level alarm. Low if it is low, alarm if it is low. Now we have the water level alarm low from 3-phase separator. Level switch 3028, which will start with having this one. Let's make another line so we're not missing it. This one will make an audible and alarm, first one, then it will close shutdown 4007, which is the 3-phase separator water outlet shutdown valve. It will close the shutdown valve at the water line if we have the low for the water. If we have high interface difference, not interface, I am not looking for, and we'll go for the condensate. condensate low, it will have this line. If we have a low condensate, it will close, make an audible alarm, first one. Then here it will close the 3-phase condensate outlet shutdown valve. It will close the same, the condensate way, same as the water did. For high, and this is the most important for me, for high 3-phase separator, take care Naja, Muhammad, Faiz. It will, if we have a high level inside the 3-phase separator, it will plant shutdown, close the inlet of the shutdown valve of the 3-phase separator, making all the 4, which is, let's go up, closing the 3-phase separator for the water, for the condensate. The 3-phase blow down will, the separator down valve will be closed, activated, and 3-phase separator gas outlet also will be activated. You will activate the 4, this 4. I am expecting a lot of questions after this one. I'm expecting a lot of questions from you. One, two, three, 4. 1, 2, 3, 4. It is simply closing all the shutdown valve on the 3-phase separator. The inlet, the outlet for the gas, the outlet for the condensate, the outlet for the water, and even the blow down, it will close it. Why? To prevent liquid carry over to the compressor and cause compressor damage. That is for the water and condensate section. Any question? Any question?
No, thank you.
Thank you. It's okay, doctor.
Okay. Oh, I am not feeling that phase.
I am okay with the cause and effect. I'm familiar with the cause and effect. Doctor.
Okay. Naja, why I'm not feeling that?
Doctor, excuse me.
Why I'm not feeling it is not okay. Is it clear for you?
Yeah, it's very clear.
Are you sure you want to repeat it again?
No, very clear.
Okay.
Interlock system, SD system. Only thing that the previously you are saying layer of protection. So first you said basic process control, then ESD control, then relief. What is that called?
Safety instrumentation system.
Blowdown system, third, and fourth PSV. So you mean to say these are different layers of protection?
I don't get it.
Yeah, you started with the layers of protection discussion, and then you said the basic process control system and ESD system. This is majorly HAZOP. We will stop HAZOP at ESD system. The other two things are there. That will be identified during the layer of protection analysis.
Let me make it for you. I understand what you said. Here is a three-phase separator, right? Okay.
Okay.
Consider we didn't have this valve, this ESD valve. Okay.
Mm.
Do you have any problem?
If you take out, then in case of the valve passing, you cannot stop. Yeah.
First one, this is operation point of view. I do not care about operation point of view at this point. I am caring about how we going to stop this equipment safely if we don't have a shutdown valve here. The question is, for example, in a HAZOP, we will say that everyone focus with me, please. This is how you can argue in a HAZOP. This will be good for you. We are assuming in a HAZOP that we are losing the control of this control valve. On another word, on a HAZOP words, we say this level control valve 53003 inadvertently open. Inadvertently mean open by mistake. Open by mistake can be because of a mechanical failure inside the valve, mechanical parts, or the instrument air coming with a high pressure may give you extra opening for the valve, or for any reason. Okay?
Okay.
That is the common words used for the HAZOP to just summarize all the failure causes of the control valve. This valve is opened by mistake. Inadvertently open mean it can be opened by mistake, human error, he put set point 100% for any reason and he forget it. The valve mechanical parts fail, so the spring is not there anymore, so the valve will be widely open, or the instrumentation air is coming have a problem and the pressure of the instrumentation air increase jump very high, causing this valve to open. The end result of the valve is that it is open 100%. That
Okay.
is the thing we are going to challenge inside for the HAZOP. That's the thing we're going to challenge for the HAZOP. You follow me, Muhammad?
Yes, doctor, but I got a headache. Just like.
Take a Panadol.
To be honest, I didn't get the point, to be honest with you. So this is in case of high pressure?
No, we're speaking about the high level, not pressure. I am trying to say that it's just imagine that
So
we
your
did
voice is breaking. Your
not from my side. Is my voice breaking, Naja?
No, it's okay, Muhammad.
okay.
Okay, it's just I will start to say it again. Please focus with me because this is very valid point and it will help you for the design. When we're making a design like this, before introducing to the client, we make something called internal why it's making this. Sorry. Why are you making like this? Okay. Here is my part. Thank you. Keep it like this. When we're making the design, before introducing to the client, we make internal HAZOP. Before we bring you as a process engineer for the client and making HAZOP for you. Simply, what we are trying to do is to HAZOP this one. to challenge the basic process control. What is the basic process control? Is the control valve here. This control valve, we assume it is 100% open and 100% closed. This is one case. This is the second case. How is this valve can be opened 100%? By mistake, human error, or by mechanical failure for the inside parts, or by the instrumentation air coming with high pressure. So we simply say inadvertent open of level control valve 5003. This means the end result that this valve is open 100%. This is what we challenge. What will be the cause? The cause will be low level. The level will going to fall down. So is there any alarm for the level going down? Yes. What happens, ya Muhammad, if we have a low level here? Gas will go blow by, going to the surge drum and make explosion. So we need to avoid this.
Will affect the surge drum.
Yes, we need to stop this. So what we are trying to do now is to make sure that there is this additional layer of protection. Layer of protection means that when the level is low, let me zoom in here. You see this one, the low alarm, it will give you alarm as an operator. Then what happens if level continue to move or to decrease? The low will activate, and according to the cause and effect, it will close this shutdown valve and make your surge drum safe. That is typically what we are searching for. My assumption was for Naja, if we do not have this one in my design at the beginning, and take care, because it is always the continuous fight between the engineering and the owners. If we didn't have this shutdown valve at the beginning, and we go for a HAZOP, and our HAZOP Sherman asks what happens if this control valve fail open and there's no protection layer, this valve is not there, simply the HAZOP Sherman will ask the engineering firm to add additional layer of protection, which will be in this case shutdown valve, to be installed here. That is simply what HAZOP searching for. That is simply the basic process control, the safety and instrumentation system for preventing the hazards of low level, high level, low pressure, high pressure in a simple equipment called three-phase breaker. Questions? Naja?
Yeah, I understood. So that layer of protection we will use when we challenge, and we'll add. Okay, fine.
Okay. Muhammad?
Thank you, Doctor. Just like at the beginning, you said in terms of sectionalizing the equipment or the unit, so we need to just like add these shutdown valve at the inlet and outlet of each equipment, okay?
Yes, this is one of the philosophies.
Okay. Okay. So, but now you said according to the internal hazard, so we need to add this. So I'm I'm still confused. Which one will come first, please? So,
Okay, if you are the principal process engineer in my company, and I come to you with a design that I have level control valve here, and I didn't have ESD valve here, and I ask you to review it, you will simply review it, asking me, Said, you put the basic process control and you didn't put the safety instrumentation system. Okay, please add the process safety instrumentation system, which is the ESD or the trip valve, and come back. This can happen internally between me and you in an internal hazard, or if you are my principal and you agree my design, when we go a third party hazard Sherman, he will simply ask you and ask me the same question. What happens if this control valve fail and we will not find another layer of protection, and we will be forced by the hazard Sherman to install ESD valve at the outlet. That's why internal hazard is very important inside engineering firms. Did I answer your question right? Yes or no?
yes, thank you. Yes, thank you. So, in terms of sectionalizing philosophy, so we will deal with it until when we will return back to this philosophy. When will we need to use it, please?
In the initial drafting. This means I am making this one, I am drawing my separator. I need to follow my isolation philosophy, so I will put this ESD here, ESD here, ESD here, to isolate this separator, isolate this volume. This is the isolation philosophy. I apply it at the drawing stage. The question is, what happens if I miss to apply the isolation philosophy, the sectionalization philosophy? This will appear on the hazard. If it internally or externally, this weak point on the design will appear on the hazard. That's why we are making a hazard externally on a third party, to make sure that all these gaps are covered. If I am not mistaken, answering your question. Isolating,
yes, sectionalization
philosophy applied in the feet. Sectionalization philosophy, we take it from the philosophy, what we understand from the philosophy in the feet, and we apply it on the detail engineering. We're saying that
yes,
we need this section valve here, we need this section valve here, there, based on the philosophy.
yes. Thank you. So it seems that relieving philosophy and depressurizing philosophy, the sectionalizing philosophy, to some extent, I feel that is interconnected, something like this.
Yes,
we can say.
Of course. They are the same. They are different faces for the same coin.
Yes. Yeah. Thank you.
You can judge how much strong the design by seeing the connection between this philosophies. If you see the connection between these philosophies is good, make sure that this design will withstand and defend against the hazard. Okay, here is the vessels. Here's what I am searching for the vessels. I will pass through it very fast. Then I will switch to the practical part for the Excel sheet, and then for the HYSYS. We can use separator to separate gas liquid, or separate gas liquid, or any solids in case of descenders. The most let's say the code for designing the separator is API 12J. API 12J have the minimum for the separators. Separators can be 2-phase or 3-phase. It can be used as a scrubber in case of suction scrubber for the compressor, or can be used as a knockout drum in case of the flaring system, which we will design our knockout drum at the last day besides pressure safety valve, inshallah. Okay. Vertical separator, typical application for it: reflux receiver if we have a tower, flash drums if we have a glycol amine units, process knockout drums or suction scrubbers, fuel knockout drum, which will be your homework, inshallah, continuous blow down drum if we have a continuous project. Horizontal separator used as overhead condensate receiver, flex receiver, steam drums, or water disengaged drums, and gas and oil separator like what we have, separation of oil wells. This is the most important part for me. We have 4 sections inside any separator, whatever the type of it, vertical, horizontal. We have the 4 sections. Primary separation sections, which is separation of free liquid in the inlet stream, which is a deflector plate, or half open pipe, or shop open to ETRA. Our second separation section, coalescing section, surge and collection section. Let me jump to this one. Here is the inlet, the primary section here, where almost 60 to 70% of the separation between the water, between the liquid and gas happen at this stage. As long as gas is going up, we have the secondary separation section, when we are using the force of gravity to catch all the droplets of the water and gas is going up. Third section is the coalescing section. When gas is going up, some of the very fine tubes, very fine droplets. These droplets may cause harm to compressors. We need to get rid of these droplets. How we can get rid of these droplets? By using this mist extraction section. Mist extraction system is coming with mist eliminator to remove all the mist, all the small particles here. This can be done utilizing the mist eliminator, which is like this one. Here is the mist eliminator part, which is like a small porous size. This small pores allows the gas to passing very fast and liquid hit on the surface of this mist eliminator. One droplet hit, second droplet come after it to hit the first droplet, making a bigger droplet. Then the weight of the gravity take it down. Here is the mist eliminator section. Here is the mist shape, which I love it. As you can see, gas enter, then switching its way, then switching its way again, then go out. Gas can switch its way very easy compared with liquid because of the moment of inertia. moment of inertia of the water or the gases or the condensate droplets is very high compared with the gas. Based on that, gas can take turns very fast compared with the droplets. Naja, do you have a car?
Yes.
Which speed you taking on turnaround?
Excuse me.
Which speed you take if you have U-turn? Turnaround, big turnaround. Consider this your car, Naja. Muhammad, you will have the bigger car.
Yes, doctor.
Faiz, you'll have the very, very big car, which is coming, a big thriller, coming with 2 cars connected. All the 3 will have this light route. The question, Naja, which speed this car can go? Can go 120 km per hour. Without this car will make an accident, right?
Yeah, correct.
This car, because it is heavier, it have to reduce the speed from 90 to 90 km per hour. This car have to reduce the speed to 50 km per hour because it is triple the weight. Triple the weight. And this twice the weight. And this is the lowest weight. This car can go to the 120 very, very easy. This is 90, this is the 50. The question is why? Why is this going 120? Why is this go 90? Where does this go 50? The answer is because of the weight. The weight of this small car is very less compared to this big car, is very, very, very less compared to this very big car. As the weight increase, the moment of inertia also increase. So when this car, big car, this one, try to go to 120, the moment of inertia is very big, so it will collapse on the road side. You got me? Naja, you follow me?
Yeah, okay.
The same here if it is go 120. This one will not collapse. It is this way, or this way of thinking for the moment of inertia was the reason for having the deflector. Here is the element. This deflector allow, here is the inlet pipeline where we have the gas, where we have the condensate, where we have the water. Gas density is 0.23, condensate density is 0.7, and water is 0.1. Is 1 almost. Is 1, sorry. 0.023. Here is the density, or consider it as the weight indication. Here is a small car. When it hit a wall, it will simply bypass the wall and go to this section. Condensate and water is very close to each other. This is 0.023 and this 0.7 and this one. So when they hit the wall, they have a moment of stop here. They stop because they hit the wall. Then the gravity effect take all the water and the liquid, all the liquid water and the condensate to the bottom section. Now we have a primary separation hold from 60 to 70% of the total separator efficiency. Okay, as long as the gas is moving all this way we'll call secondary section. Then here is the gas outlet. We want to make sure that gas will have minimum water droplet. This can be done by using mist extractor, where, as you see from the picture before, here is the mist extractor inside shape. So gas will go all the way till it reach out. Water will not be able to follow the same path as the gas. So water droplets will hit here, then another gas come, then another water droplets come, then it will drop by gravity. Here. This called mist elimination. Take care, because mist elimination have delta B and have micron size. Why, Muhammad, we are interested in this? Because we don't want to make extra delta B on the mist eliminator. That's why we take the K values from the vendor and the micron size for the droplets, for the liquid droplets which is coming out of the gas. Can we eliminate all the droplets? No, we cannot. So depend on the application. If this gas is going to a compressor, like our case, so we will be happy if we have 25 micron of gas, of water droplets or liquid droplets inside the gas. We'll be happy if we have this limits. But if this was a knockout drum of a flare system, this can be more than 600 micron for the mist extractor. 600 micron, Muhammad, mean
Excuse me, you're asking me?
yes, I am telling you.
Yeah. 600 micron, which is multiplied by 10 power to minus 6.
Yes, if you want to convert it. 10 to the
Yeah,
power
so what
of
is
10 if you want to convert it to meter.
So what is the question, sorry?
It is not a question, it is just I want you to make sure that you focus. 600 here means that the size between this steel plate and this steel plate is the 600. So you will only, if you have a gas continuous droplets with 650, it will not pass through the mist eliminator and it will condensate at the bottom. This number is acceptable for knockout drum. 25 is number acceptable for a compressor applications, and 150 is acceptable for fuel system. Everyone write these numbers: 25 for a compressor, 150 for a fuel system because it will be your homework, and 600 for knockout drum. Now, we have here water plus condensate is coming. Let me put it in a new so we can write. Here is the water plus condensate. Naja,
Yeah.
we have a problem. What is the problem? Here is the inlet. Here is the outlet. Condensate and water. What simply we want to do is to make sure that we give a good time for the water and the condensate to be separated. Okay. You follow me, Naja?
Water hydrocarbon is being separated in the first compartment, okay?
Yes, we need to make sure that we have a clear interface between the condensate and the water. So, on another word, if you at your home and you have a bottle and you have a water and oil on the top of it, if you didn't shake it, you will have a clear interface between them, right?
Yeah.
This is the optimum. What we want to receive it here. We have a clear interface between water and condensate. Condensate just jump over the wire going to this compartment. That is the optimum for us to have a clear interface.
Okay.
Now let's take this bottle and shake it. Shake it for 20 minutes. If you shake it for 20 minutes, it will take almost between 2 to 3 minutes to back to the optimum. To back to the optimum, which is a clear interface between oil and water.
Okay.
If we shake it more for 2 hours, it will take between 10 to 15 minutes to go to the optimum. Now, consider yourself the water and the condensate. You coming out of the reservoir underground all the way to the Christmas tree, then from the Christmas tree all the way to the pipeline till you reach the separator. So you have shaking time more than what we just mentioned, or more than all this. You have a very big time. So if we give, what time should we give to them? Until we get a clear interface between water and condensate. Typically, if we have all this shaking, you can end up by a settling time, or yes, let me settling time between 1 to 2 hours. This is the theory, Naja. This is the theory. 1 to 2 hours until the separator have a clear interface and it can operate. Is this practical? No, it's not practical. So what we do, we accepting some here water to be 95% and condensate to be 5%. We accepting here condensate to be 95% and water to be 5%. We accepting these conditions here and there to assure that this time reduce from 1 minute till 25 minutes according to 5 minutes, according to the applications, which is called the retention time. Retention time is the time the fluid count when fluid enter from this flange till it is out from this flange. On another word, the time of staying inside the vessel. This is the retention time. Why we said 1 minute? Why we said 5 minutes? Based on what? Based on two things. Now, Naja, consider yourself this is the droplet of water on here on the condensate side. It will be surrounded by a lot of condensate droplets, right? Naja,
Yes.
okay. What we are trying to do, this condensate droplets trying to make tight connection over the water droplet. Now, which forces want this water droplets to go down? The gravity and the weight. The gravity force wants this water droplets to go down, and the weight of the droplets will determine how much velocity it will go down. On the other hand, which forces take this water up? It's called beyond force. This is the force which making by the condensate droplets over the water droplets to take the water droplets up.
Yeah.
Simply, what we are trying to do, Naja, to making the forces for the gravity and the weight much higher than the beyond force. How we can do this? If this water droplets became larger. How it can become larger? If it is meet another droplets. If it is meet another droplets, this droplet will merge with this droplet, making a bigger one. Then the gravity force and the velocity will be higher, and this droplets will go down. This is called settling velocity, which we are calculating, Naja, to determine how diameter, what will be the diameter for this separator I short sized this separator based on one diameter to give the droplets the velocity, the droplets the time it is need. Based on what? Based on the velocity of the droplets. On another word, Naj. On another word, Muhammad. I assume a weight for the droplet and I calculate the settling velocity. It will settle down because of the weight, and this velocity is meter per second. When I multiply it by the retention time I give it, which is 60 seconds or 60 multiplied by 5 minutes, then I bring the meter, which is the distance here. I should make my diameter twice this distance. You got it, Naja, or no? Little bit hard, right?
Yeah, the velocity V is the flow rate coming into the vessel, correct?
This is a what?
What is V, meter per second? What is the velocity? This one?
Velocity is the settling velocity. The settling velocity
Settling
of the droplets here.
Oh, okay.
Okay. Let me go to the presentation again and I will have one clear example. Here we are speaking about Naj. Here's the droplets. There is a drag force on droplets to take it up. This force is calculated by the CW multiplied by the area to the power half rho V square, where CW is the drag resistance coefficient, which we bring it from the Reynolds number. How much the flow is giving a resistance. Practical area perpendicular to direction of flow, meter square. Density of the fluid and velocity of the droplets. Then we have the gravity force, which takes the drop down, which pi over 6 by d droplet diameter multiplied by the distance difference over the g. G is the acceleration, 9.81 meters per second. Rho b is the density of the particle, density of the droplet itself, gravity force, which is the Fg. This is a general theory. We simply want the gravity force be higher than the drag force. That's what we are trying to do. Okay. Here, from this table, we can extract the dragging coefficients by using the CW. CW, as we said before, here is the drag resistance coefficient, CW, and CR square. When we are making this one equal this one, this means the droplets are constant, so we can bring the CW from the formula. Okay, I don't care about all of this. Then, by the end of the day, he making the velocity is a variable between the K and the B, the density of the droplet minus the density of the liquid over the density of the liquid. Go down. Now we are calculating the maximum allowable vapor velocity. There's two equations, Sanders-Brown equations and pressure drop factor. We are going to speak about it. Here we're calculating the velocity. Once we're calculating the velocity, which is a function of the K, which is the corrected vapor velocity constants, which we are bringing from the tables, multiplied by pressure density of the liquid phase minus density of the vapor phase over the density of the vapor phase. Then we get the velocity. K corrected can be canned from the K design maximum multiply the BFD BDF multiply by design approach over 100, which no one doing it like this now. We simply making this like this. Pressure derating factor for operating pressure more than 2 bars as a design approach. I feel that you lost from me, Naja, right?
No, it's okay. So we calculate VA from this equation. Fine.
Okay, the key corrected. What we are trying to say that design approach is because of that design inconsistency, or the design maybe have a mistake, so we add the design margin. Pressure derating factors is a factor for the pressure because not every gas follow the ideal gas law, which PV equal nRT, so that's why we make a correction for the pressure. And K design we have it from the tables. That will be give you the K corrected. From the K corrected we back to the equations. Here is the table for the K values. We take it and put it back here to get the K corrected against the pressure. K values is coming from vendor or coming from GBSA data, which we have it. For example, if you're going to high capacity mesh pad, if you have mesh pad for the mist eliminator, if you're using style 1940, you will have a K value equal 0.35 feet per second, or it is 0.107 if it is meter per second. Derated for pressure, yes. Derated for pressure, derated mean it is need to be calibrated for pressure, yes. It is performance affected by the pressure, yes. So you need to make a correction for this 1.107 by utilizing this equation. Then you take it here, you have the BFD, then the design approach, you bought it 95% or 10% if you want some margin. Then from the K you bring it from the table here. It's a simple way forward to install it on the equation. Okay, I will skip the questions. I don't know why is this coming here. Let me put it back. Here is the vertical separator, here is the horizontal separator. All of them, all the three, are depending on calculating the velocity of the gas entering and the settling velocity of the droplets. Here, Hamad, Naja, Faiz, we have three velocities. What velocities we are speaking about is, let me go, gas velocity. Gas is moving all this way, so we need to calculate the gas velocity. 1, 2, we have some water droplets going down from the condensate side here, the water, and this condensate droplets want to go up from the water side. Then we have condensate velocity, then we have the water velocity. We calculate the three velocities. Always the water velocity is the least. Is very low. Let's make it low. Based on that, we sizing the diameter of the vessel. We sizing the diameter of the vessel. Here, a lot of equations just to calculate the droplets. V absolute equal V corrected multiplied by rho liquid minus rho vapor over rho vapor, all the to the power of 0.5. Okay. For you, Muhammad, Naja, anyone who is going to design a separator, you need to know pressure of the stream, temperature of the stream, flow rate, physical properties, degree of separation requirement. What is mean by degree of separation? It is mean how much you want entrained liquid in the gas, how much water you want in the condensate, how much condensate you want it on the water side. Our design factor for a vessel, required line surge resistance time or flow basis. Resistance times is being depending on the application. We're going to speak about this. Any other effect is if you have a forming system or anything. Let's go to the specs. Here is the steps we are going to follow. We have almost 6 steps we follow to make a separator design. First one, which vessel we are speaking about. Determine type of vessel. Is it gas liquid or 3-phase separator or liquid? Hold up time. Do we need hold up time? So our separator work as a tank for make sure that there is a level for the pump, like in the surge vessel in our case, or it will be a low surge tank, a low hold up tank, like our 3-phase separator. Plant consideration, if there any plant consideration, if a plot consideration, if there are any problem in the plant layout, if it is offshore, for example, and there is no fingerprint or equipment print or food area, the area of the separator is very restricted, so we need to make it a vertical one, not a horizontal one. And type of material we are going to use for constructing this separator. Do we have any H2S problems? Do you have any H2S problems, or we can use a carbon steel? Step 2. Determine the vessel minimum diameter and dimension. Minimum required diameter for gas liquid separation. This is a vertical, and for a horizontal one, minimum required dimension for vapor space height for gas liquid separation. This is at point 2. Hold up time required. Adjust vessel diameter or length as required. Here is vertical one. Fix minimum diameter from allowable vapor velocity with mine how defined for liquid hold up. We're going to make it this horizontal vessels, assume diameter and length, then calculate the vapor space criteria. Here we are some of the guidelines. Take care, Naja. Hamad.
Yes, doctor, yes.
Did I increase the headache? Yes, I know it is boring.
No, it's okay. Thank you.
No, no,
But
I know it is boring reading from the slide, but we have to do it because it is the basis
No, in
for
fact-
the Excel sheet now.
it is interesting.
Actually, Doctor, you don't appreciate those formulas unless you start applying them
Uh,
to understand the relationship.
yes, but the good part that I am sharing with you all the Excel sheet which we used in Wally Parson. Typically, these equations, let me go up, what you can find on GBSA, which is a typical handbook for oil and gas. If you go to API 12G, you will find the same equations. This equation is not interested as the practical side. The Excel sheets which we're going to present now have this all equation on the background. Is it important to know the equation? Yes, but the most important for me to make sure that when you are reviewing or you're making a design, the critical point like what? For example, in any handbook, he will tell you that the length over diameter for a separator should be between 2.5 till 5. The dimension, the length over the diameter should be from 2.5 to 5. But no one telling you why. You get my point, Faiz?
Yes, yes. So people, they put the criteria, but what is behind the criteria usually is not explained.
Exactly. Here is the mechanical reason. A long vessel needs stiffness ring. Take care. Stiffness ring mean extra ring of metal will be surrounding the vessel, which will make them more expensive. Thus make your separator exactly double or twice the price. If you make L over D higher less than 2.5 or higher than 5. So from mechanical perspective, and take care about this one. If you are working below 3 bar G, the optimum LD it will be 1.5 to 3. I don't care it. This equation phase can give you more than 1 L over D. When we are solving one of the separators, it will give you many dimensions, can give you the retention time and the velocity for the gas and for the liquid. It will achieve your process objective to separate the gas from the liquid. But none of them, except 2 or 3 options, will satisfy the mechanical reasons. So it is optimum to have 1.5 till 3 if you are below 50 psig. It is optimum to have if you're going to work from 3 bar G to 40 bar G, 3 to 4. If you're working higher than 40 bar G, you can jump till to the 5, but never ever exceed 5. So here's another equation for what? For determining the diameter. Here is the velocity of the liquid. We can simply take it from settling velocity formula, which is Q liquid over 1 over 4 pi d square, which equal to 2.2 multiplied for the power 10 to the power of minus 8 multiplied by rho liquid negative rho vapor over the viscosity. This is the gassing for vertical separator. Is it different from a horizontal separator? Yes, only difference on the numbers. But it's all the same. Here is the mu, here is the rho, here is the rho, here is the q, everything is the same. Except here we are introducing the length of the vessel. In a vertical, we didn't care about the length, we did care about the diameter. In a horizontal, we take care about the length. Okay. Here, some safety factors we was learning in our starting life. 0.7, 0.8 is the safety factor you're taking when you're making a design. If you're making a design, jump to 0.7 if you are new, 0.8 if you are old enough and your design is competent. It's called safety factor. Anyhow, here is the vertical gas liquid separator. You can use this formula, or you can use this formula for horizontal one. Here is the most important part for me. Can you write this phase? Read this. Phase.
Yes, doctor.
Can you read from here? All this.
This is about operator response time.
Yes.
You want me to read
Yes.
the paragraph, you mean?
Yes.
Yeah. The time required by the operator to react between maximum liquid level and high liquid level, or between minimum liquid level and low liquid level, typically 1 minute, unless the project design philosophy has stated different.
What does this mean?
You are giving only 1 minute for the operator intervention between the low and the low and between the high and the high and low, or level.
Is that enough for you?
No. It doesn't make sense. 1 minute is very strict.
Let me say in this way. Everyone see my white screen?
Yes, doctor.
Okay, here is the separator. Here is the low, here is the low, here is the high, here is the high. What phase read a few minutes ago? The intervention, or the time between low to low is 1 minute. Between the high and high is 1 minute. Right phase?
Yes, that was the criteria or the requirement.
Totally right. Now consider this one give you a diameter 3 meters for this criteria. Increasing the time here and there, let's say how much time you want phase.
You want realistic time for the operator
Tell me.
to notice it and then to take the corrective action.
Tell me, here is your operator. How much time he need?
It depends. Depends on the equipment and the distance but not less than 10 minutes. I would give the operator
10 minutes?
5 to 10 minutes. It's okay. 10 minutes.
Okay, 10 minutes. Based on what you give this 10 minutes?
There is different criteria for different company, but usually I would consider how much time you will...
No, there's no different criteria in this.
Excuse me, doctor.
Yes.
I think I got Mr. Faiz's idea because he thought that maybe, correct me please, Mr. Faiz, just like my understanding is correct or not. So he thought that is in the field, so the operator needs to take action. But what we are talking about in the control room itself. So the operator is still just like seated instead of the screen, and he can just like control it straight away. So 1 minute is okay, Mr. Faiz, for this such scenario to take an action if he is
Yeah.
available. Yeah, if he is
But
available.
yeah, even inside control room, I mean, there will be a lot of alarms. So 1 minute still strict for operator to take action because he
Yeah,
will
but-
deal with many responsibilities and duties.
But we don't have just like much time that you are talking about, because in order to the separator to be full incompletely, it needs 3 minutes. Okay, so the time to transform. Excuse me, Dr. Sayed. I'm just trying to reach the idea to Mr. Faiz.
Take your time.
So thank you very much. So to just like get from high to high, it needs 1 minute. Okay, Mr. Faiz? From low to low, it's 1 minute. So we already have 2 minutes, just like subtracted from the total time, which is 3 minutes for the separator to be full. So what is the time left by just like subtraction, the 3 from 2, 1 plus 1. So we will just like get 1 minute. This is the range between low and high that the operator intervention is required. So you got the point, Mr. Faiz?
Yes, because here you are putting a limitation 3 minutes, but reality 3 minutes is very stringent.
Yes. For this reason, the response should be just like taken just like in very quick way.
Because you need the operator just monitoring the system, not doing anything else. Because you have only 1 minute to react.
Yeah, they sit all the time in front of the just like screens, just like monitoring the conditions of the process variables. So this is everything that they should do. Hope this clarify the point. And sorry, Mr. Dr. Said.
No,
I'm just
take your time.
trying to explain it for Mr.
I
Weiss.
love intervention.
Thank you very much. Thank you.
Faiz, yeah, Faiz.
Yes, doctor.
How are you?
Yes, doctor. Go ahead.
How are you?
Alhamdulillah.
Alhamdulillah. Let me clarify something. What is important in a separator? Pressure or level?
What is that, sorry?
What is important in a separator? Pressure or level?
Well, it depends on the type of separation. So, but in this case, the pressure is not variable. I mean, the pressure will be fixed. You will fix the pressure, isn't it?
Yes, we also fix the level if it is the same concept.
I think the level is more.
You mean the most critical? The most critical?
I think the level.
No. In any separator, the pressure is the most critical. In any tank, the level is the most critical.
The level is most critical, yes. But I mean, doctor.
In any reactor,
but
if we have a reactor, the flow rate is the most critical. In any heat exchanger, the temperature is the most critical. On the other hand, Faiz, when you ask for 10 minutes, 5 minutes, or 15 minutes, these three numbers is coming under API 5225, API 2255, which is giving you the level of concern. That's used for a tank. That's used for tanks. To telling you that the distance, take care of about what I'm saying, the distance between your operator which is sitting on the DCS till he getting up, moving all the way to the tank, make the correction, the high level to the high, to stop or close the inlet valve and switch to another tank. If this is the case, based on what? Based on the distance between your DCS and the tank. You get my point? This 15 minutes,
Yeah, clear.
this
Doctor.
10 minutes, this 5 minutes is going in an equation in ABI 2255 to saying that I will put the high alarm on level X and high trip will be X plus 15 minutes or 10 minutes or 5 minutes based on the distance. This is happen in the tanks.
Yes. But for from our side, actually, we start. I remember we did this exercise in the tank. We also applied the ABI criteria.
Good.
But really, we start thinking differently as a philosophy, that we make the duration longer for the operator to react, because there are shift changes and many things could happen.
I don't have
So
any
we
problem
feel-
with this. I have a problem with one
Yes,
thing.
so for tank, for example, 10 minute or 15 minute, I would say it is stringent, and we try to make it more, more duration for the people to react.
Do you know the problem is? If you make the duration here, let's say 1 hour, is that good 1 hour?
Yeah, let us say 1 hour, yes.
Okay, that means your instrumentation engineer will take this level here from here, which is set at 15, and make it here. To start alarm you 1 hour as you want before it reaches high. The problem is, Faiz, that here we have all this as operating envelope. This means the capacity we can store in this tank is all this each. Now when we're moving to this one, the capacity reduced. You get my point?
Yes, I understand. Yes. But
that's
considering
why. That's why.
Yeah.
The ABI could give you from 5 to 15 minutes, and he mentioned on at the end of the code that you can extend the 15 minutes based on the distance between the control room till the operator reaches the tank and takes the corrective action. So if you want to increase the 15 minutes, you have to ask a physical practice. Once the alarm here, and you ask your operator to stand up from the DCS and move all the way till he reaches the tank. Calculate the time and recalibrate your high alarm based on that. You got my point?
Yes, very clear. Yes, very clear. So here we are assuming that operation discipline is well enforced, and 15-minute people, they will comply with it timely and all of that. And
what is the distance
but
between your
really
DCS and the tank?
Victor, 15-minute. Really, I was in the management rule. 15 minutes, I don't feel comfortable. This is why we make it longer duration. Because
can I ask you, Faiz, what's the distance
yes,
between?
expense of the capacity, but really give us more assurance.
What is the distance between the DCS until you reach your first tank? 1 kilometer, 2
Yeah,
kilometer?
yes, I understand what is behind this. Yes, let us say 10 minutes. I understand this.
Thank you.
But what happened in real operation is something different, Doctor.
You need to train your operation to respond fast. It is not a design.
We did that. We did. we did. This is the API. We consider it the minimum requirement.
Yes.
But we tried really to compromise the capacity to ensure that really we don't end up
That's mean
with incident.
you are not utilizing your capital cost if you're utilizing your tanks.
No, yes, there is compromise, but
Up
I
to
mean,
you,
safety is
Faiz.
first,
By the
because
end,
the
Faiz,
incident in the industry
Faiz.
is huge for this tank overflow.
Yes, by the end of the day, you have to train your operator to respond in this time, because it is the most common time. But if your operator was in the bathroom and the alarm is sitting, he will not be leaving the bathroom until he finish. So it is better for him and for anyone in the control room that there will be someone in the area. He can just radio him, please switch from this tank to another tank. This is the most important part for me. That someone to take the response. The code, the API, taking it from the worst case, assuming that there is no radio, and the operator sees the alarm on the DCS, and he have to leave his chair, moving all the way, walking, not running, till he reaches the tank. Then he's making the switch. So 15 minutes is more than enough, especially if we are speaking about small layout, not a big layout. In refineries, when I'm making the design, I make it for 20 minutes, because refinery
You
is
see,
very big.
Doctor, most these problems happening during, for example, startup cases where people busy with a lot of activity, with the shift changes, with many things.
Up to you.
This is my observation. So, and this is what I experienced in many cases. It was part of a big number of investigations. And yes, we think this is stupid, but in real life, it happens.
I don't have a problem with real life.
all this, gaps or
You have a
happens together, and then you end up with incident.
you have a problem with your operators. That's all.
This is
They have to respond
it's
more.
not our operation only. It is all around the industry. It is
uh,
a continuous effort to ensure you have competent operation.
Faiz, I am coming from operation background. I work as a shift engineer for 8 years in my life, so I know what I'm saying. Make your operator run fast. Don't try to tell me that all
I
operators are
understand
bad.
that, but reality there are many things that could go wrong.
Yes.
Real life.
Yes.
Real life. Many things can go wrong together.
Yes, totally right.
Yeah.
But
Very good.
So once the incident happens, everybody starts, how it happened. This is very trivial. What did
yes.
go wrong? But real life is different, Victor.
Okay, make
I
sure.
mean, it depends case to case, from tank to tank, but real life really different. Yes, 15 minutes is the minimum requirement, but really, if I am the production manager or the process engineering manager, it's really doesn't make me feel comfortable.
Okay.
I try
Faiz,
to make it more conservative.
Faiz. By the end of the day, it is your plant. By the end of the day, it is your tank. No one will, will causing you that you are making not a good operation when you overflow the tank. If you overflow the tank, many people will just causing you that you are not competent and all of this. In any accident, there will be a lot of people saying that how this fault happened. That's not the case. We are trying to avoid the mistake. If you utilize 1 hour and you train your operator for this 1 hour, I will be happy. Me myself, I will be more than
we are
happy.
not training the operator for 1 hour.
Perfect. Let me complete the sentence. Just
Yes.
if you train it for 1 hour, I will be happy. But the problem is that if you train any human for 1 hour or for more than this or less than this, the response time will be depend on how much space you give it him. For example, what I did in my plant is I size it for 15 minutes and I train operator for 10 minutes. You got my point? When I leaving the operation live, going to engineering, I told them it is sized for 15 minutes, not 10 minutes. And all operation scenarios for emergency response was being trained for 10 minutes, not 15 minutes. You got my point, right?
Yes, clear, doctor, clear. Actually, this is the way we handle it. We are trying to, we train the operator to immediately respond to the high alarm, right? And any deviation, for whatever reason, it cannot be managed. We have multi-layer system like alarm system, key operating parameter system, critical operating parameter system, all of this system in place. And for any reason, operator cannot address this limit, the operating window, he has to go to approval, high level approval, high authority approval.
I get your point.
Yeah, so we have really, it is learning over the years. I have seen a lot of learning. Even, doctor, to the extent some tanks, we think it's trivial, but some tanks, they don't have, as per the original design, they don't have, for example, automatic XP to close in the case of high level. And we incorporated this as part of the design. It is learning over the years.
Yes, I see the same problem in all the plants in Qatar Gas and in Aramco. In Saudi Arabia, we have a lot of plants like this way. Because all the design, they don't have the XVs, so we have to give on-job training for the operator on how to respond in case of high alarm because there is no XVs. I was sharing this.
And eventually, doctor, we added for all these tanks that is doable to add the VSV XVs, we added XVs, we invested in the XVs.
You have money.
Because no, it's not about money, it's about if incident went wrong happens, the cost is
Yes.
it's really
But not all of people doing
consequence
this.
is very high. It's very severe.
Not all of people
So you
doing
cannot
this.
really you cannot really accept such consequence.
Yes. Do you know the tanks in Saudi Arabia? Take care, Naja. Naja, focus with me on this. We have the high, we have the high, and here is the feed to the tank. There was only a manual valve. This manual valve has the same, another here, manual valve, another tank. For switching between tank A and tank B. And here is the pump, which is pumping from the tower. Naja, are you following?
Yes.
Normally, this one is open, this one is closed. We're filling this tank. Then, when this tank is filled, we close this one, we open this one to filling this tank. This tank on this time is going to offloading or dispatching to the customer. The typical accident here is overflow. Copaco in Colombia have a terminal, oil terminal. This oil terminal exploded in 2009 because the overflow here was like 1 hour draining to the ground. 2009, 30 tank explode. So for you, Naja, if I want to close this one, make sure that this overflow will not work. I should make a control loop as Faiz did to make ESD valve XV, not manual valve, right?
Yes.
And it should be initiated with the high
High level.
to make an interlock, and from this interlock to go to the SD, right?
Yes.
Is that what you did, Faiz?
Yes, correct. Yes.
Yes, there's something missing for me. If you make an XV here, you have to make another XV here.
Yes. Yes. So change over.
But there's
Automatic
also
changeover.
something missing. What is the missing?
Automatic change over.
Yes, the changeover, exactly. You cannot close this one and close this one. You have at least to make sure that when you're constructing your cause and the effect, that there is one close and one open. To make sure Faiz is always a way to this pump. There's an open way to this pump. That's why if you have a tank terminal or a group of tanks, let's say 10 tanks, you have to take 10 XVs. You cannot select phase, take care about this. You cannot take 5 tanks to make them XVs and other 5 tanks on manual mode. It make a lot of accident phase. You got my point, Faiz, or no?
Yes.
Oh, Naja.
You should consider all scenarios, not a few tanks and you leave the other tanks.
Exactly. Okay, let me open the Excel sheet for the HYSYS. Yes, let me open the HYSYS first, then we'll go to the Excel sheet. Okay. Let's share. Do you see my HYSYS?
Yes,
Okay. That's what we did.
but execute with black screen, still black screen.
Everyone see black screen? Hello? Hello? Everyone see black screen? Anyone reply to me?
Yeah, black only.
Is it still black?
Yes, it's okay now.
You see the equipment? See my mouse? You see?
Black again.
I don't understand what happened, actually. Here it is. Okay. Let me change the background to see if it is me.
It's okay now, doctor. Okay, okay.
What you see now?
Yeah, it's fine.
Simulation option.
Okay, it is not what I want to see. I just want to see the how. Now it's black again, right?
Yes.
Okay. Naja, can you open the HISIS please at your side?
I have to log in other computer. Anybody other person having, or I'll go and log in.
Okay, Muhammad,
Okay,
can you
I'll go
open
and
your
log in.
HISIS? Muhammad.
Yes, doctor, yes. Just a minute, please.
I don't understand how this happened.
Before it appears, the equipment,
What?
we have seen some equipment and then disappear from the EP. No, not this one. It was like, yeah.
I don't know why. Don't know what is the reason. What's the relation between HISIS and it's black now, right?
It's black now, yes. I think it has to do either by formatting or customize. One of the.
Doctor, the software is ready if you like something to deal with it. My screen.
Okay. Can you share and give me control, please? Yes. Request control. Yes. You don't have our case? Hello, Muhammad. Muhammad. Hey, should have started from the beginning? No, it will take a time. Okay. Muhammad. Muhammad.
Yes, doctor. I couldn't just like make the mic unmute because it was under your control. Okay.
Okay, I will drop you one file on WhatsApp, which is, can you please open it?
Okay.
Okay, meanwhile, we will use the Excel sheets till Muhammad finalizes this one. Okay, make mute Muhammad.
Doctor, some
Yes.
of the folder sorry.
Yes, tell me. Yes, Faiz, تفضل.
In the drive, some of the folder Excel calculation and the folder is empty. I'm not sure whether it is only my problem or everybody else's problem.
Do you have any problem with the folder which I uploaded to Google Drive?
No, in Google Drive, you open the folder, I download it, no problem, but the folder inside is empty, or doesn't contain any Excel tools. Some of the folders.
No revision calculations?
No calculation sheet, yes, some of the folders. Some of the folder it has, but many of them, they don't have calculation tool, Excel tool.
Okay, I will upload it again, not a big issue. One of the things you will find for the Excel sheets is the three-phase separator manual. How we can use this one. This is the PDF. Naja, are you following? Muhammad, are you following?
Yes.
Okay. This is what you see if you choose a horizontal three-phase separator. That's what I want you to read. Here is the instruction part. Here is the filling part. Here is the go to instruction, show active, show all these parts. Here is the numbers we are filling. Here is the basic assumption we are input. Here is the fill in section for the process input data we are going to do. Here is the design data and assumption we are filling inside the Excel sheets. Here is the physical configurations. Here is the drag coefficients which we bring it from the equations. Here is the k values. Remember the k values we speak about? Here is what we have, bring all the k values inside it on a table. Any configuration and the misters from the vendors, if you are working with Okaya for example, or any other clients or any other vendors, you will bring their their K values. You will bring either the Mr. thickness, height of allowance above diameter, minimum vapor space below diameter, if we have a Mr. Only configuration, inlet configuration. Here is the liquid micron we are interested, 100 or 25 or 600 or 300 depending on the application you are bringing. Here is the 1 minute مع فايز, or you can input 10 minutes. What I will do now,
والله يا دكتور I'm still see 1 minute useless from high to high.
let's it's your task. It is your task now. It is your task now. You will make this 1 minute when you're using the Excel sheet. You will make it. Okay, Muhammad, I will ask Mark. Your task, they will solve for 1 minute, and you will solve that for 10 minutes. Remember, Muhammad, in page 17 on the PDF, you will have 10 minutes. Okay? Okay?
Excuse me, sir, just like the internet was interrupted, so I didn't follow you.
Okay, Muhammad Faiz, you will making this 10 minutes for your calculation for the emergency HHL. Page 17. Just take note, Muhammad, and I will making all this again.
Yes, doctor. Thank you.
Okay. Now let's share the Excel sheet. Everyone sees the Excel sheet?
Yes, no.
Yes or no?
Yeah, it's just coming.
Okay. This is a horizontal 3-phase separator. The same what we have on our project. Here is the instruction. As you see on the BFD, which is attached, which I uploaded to the Google Drive, you see the same word. Here is the cover sheets for the calculations. The cover sheet for the calculations. Here is the calculation checklist. Please remember the calculation number assigned, project shown, calculated title shown, receive history books complete and assigned, table of content. As you making each one, you take it. Not our issue today. Terms and condition, table of content. If we have any content, please mention it. If we have any assumption, please mention it. Of course, if you're working today with a Wally person, you will put the customer name, the project title, calculations title, and the location where you're going to save this file, the project number, the calculation number, the cost time resources, CTRs, result summary, and 3-phase empire. What is this? The same for the project. Then we put the input data. The vapor, the liquid, light liquid, the heavy liquid. The vapor stream identification will be the name, you name it for this stream. In your simulation case, on your PFD, whatever you want. Let me guess. Liquid, light liquid will be condensate. Heavy liquid will be water. Everyone following me, please?
Yes, doctor.
Okay. How much mass flow by libra per hour we have? What I normally did when I was a junior engineer, I was opening my simulation, bring the number, put it here back. What I can do, if I am the owner side, I just take the numbers from the flow meter at the inlet of the plant and insert it here. Let's say we have 10,000 libra per hour for the gas, we have 50,000 for the condensate, and let's put 30,000 for the water. The density of everyone for the gas is 1 libra per cubic feet and 50 libra per cubic feet if it is water. Viscosity is already mentioned, 0.1 for the gas, 1 for the condensate, 2 for the water. Based on that, these figures, he calculate the first equation we see in the presentation, the Q quantity of gas by feet square over minute. Remember, vapor mass flow, Naja, the same as we say in the PowerPoint. Vapor mass flow over 60 by density vapor libra feet square multiply 1 plus design margin, which we bought as 20%. Then you have the water flow, the condensate flow. Both we have. Section 2, which pressure we are operating at, which pressure temperature we have, corrosion allowance, minimum vessel thickness. Which pressure we have? Naja, your homework will be 250. Hamad, Faiz, Hamad,
Yes, doctor.
your homework will be 500 BSIG. Faiz,
Let's go ahead, please.
you will have 900 BSIG at this Excel sheet as a design pressure. 900 for your side. Okay, everyone write after me, please. Naja, you have 250.
Yeah.
Muhammad, you have 500. Faiz, you have 900. Okay.
Okay, doctor. Okay, thank you.
Okay, Muhammad, you will have a design margin 10%. Naja, you will have a design margin 20%. Faiz, you will have a design margin 30%. Everyone reply to me, please.
Yeah, 20% for me.
You are Naja, 20.
Yeah, 20.
Yes.
250 PSIG, 20 bar. Okay.
Faiz,
Yes, it will be 30 in my case, the design margin.
yes, thank you. Track coefficients, we all have. Here is the K values coefficient or the drag coefficient. This is the two ways of sizing the separator. GBSA use K values, Wally Parson use drag coefficient, which is more conservative. More conservative means they are very tight and they always give more space for the water, which is good. Target liquid droplet for vapor liquid separation. In your case, Naja, you will have a micron size for a separator. Real separator will be 50 micron. 50.
Okay.
Muhammad,
Yes, doctor.
you will have 150.
150 micron.
Yes. Faiz, you will
Thank you.
have the 600 as a knockout drum. Okay. This is acceptable for the gas. We are accepting liquid in the gas like this one. This is acceptable for droplet diameter assumed in heavy from light. This is how much condensate will be on in the water. 100 micron is more than enough. I don't love it 100 micron, but keep it like this way. Okay. Here he calculates the settling velocity based on he have the 1 over the length over diameter 1 to 6. 1 to 6. I don't love 6, so I put it 5 to make sure that it is follows the GBSA. Based on that, Faiz,
Let's go ahead, please.
how much time you want the top of the vessel to be above the high trip?
You mean between the high and the high alarm?
No, between the
The emergency alarm.
high and the top of the vessel. High trip is being like 0.9 of the total vessel height, right?
The high, it will shut down anyway, right?
Yes, but what happened if it didn't shut down? What happened if the system failure? Do you want any space above the high, or should it be on the top?
Yeah, we should have some space, yes.
How much space
Usually
you want?
they keep some space.
How much do you
Yeah.
want? How much inch you want? Or how much time do you want?
Half an hour to 1 hour.
Haha, 2 hours?
No, too much 1 hour.
2 hours, this Excel sheet will not solve.
For a separator, too much.
Yes. The default number is 0. The default number for inches is like 10 inches, oh, not sorry, 2 inches, which is 5 centimeter, 10 centimeter maximum.
Okay.
But for our case here, we'll keep it a minimum. Okay. Then, here is the levels we want to put. Take care بقى. Take care. Minimum interlock search between high and high. How much time you want, Naja?
High and high.
Yes.
Can be like anyway, it depends upon what kind of tools available for operator to notice it and do some actions. So it can be like 1 or 2 minutes.
2 minutes. Or
2
you keep it
minutes.
6 inch. Which you want to love? Based on what I'm asking you? Based on high allowance above the mystery. Sorry. Based on the response time of the operator.
Yes, response time.
2 minutes is more than enough for a operator.
Yeah.
Okay. Muhammad. Between the normal level and high.
Yes, doctor.
How is the headache?
It's okay, doctor.
No, a lot of information, no? So it's good. A lot of information is going to Muhammad.
Yes. And it's just this all easy, very easy compared to if you make it in HYSYS. But HYSYS didn't give you all the details as Excel sheet. So let's keep it one for every thing here. When we have ones, what type of heads we need? Heads mean the head of the separator on the right, on the left. Is it elliptical side or dish side or flat or hemisphere? Hemisphere is the most recommended one because it's easy, very easy on manufacture compared with the flat one. Okay, all this calculation he calculated by default. Then let's go here. Here is the shape of your separator. I will click update the graph to have all this number. Total volume of the separator, liquid volume for the condensate, for the water, total dry weight, total weight if it is filled with water, high, low, 3 feet, high on 3 meter, and normal level will be 2.5, low will be at 2 meter, low, trip will be 1.5 meter, based on the 1 minute we bought. Diameter, why didn't you give us a lens? Let me calculate this one. Two. The ironic part that I solved it before the course. It was solving and no problem. It's solving all the way. Don't know why it's not solving. Whatever 2 kilometers. Thank you. Hello everyone. Hi. Hello.
Hi, Doctor. Hello.
Yes. Here is the run, Muhammad. Here is the runs. Here is the calculation he make it at the background. There was one of the equation have a mistake.
Yes, Doctor.
I don't know why. But the L over D is 2.33, which we selected to be 12 feet length over 4 feet diameter, which when we update here it should come up as here the high 7 feet, the 6.5, the 6 5.5, and the 5 at the low. This is for the liquid side, for the interface side, and this is for the condensate on the other compartment here in the bottom side, and this is the nozzle dimension according to the velocity. That's okay. That's all for me. Muhammad, can you share your heises?
Yes, Doctor.
Okay. Everyone can see Muhammad's screen.
Yes, we can see, yes.
Okay. Here is this three-phase separator. The good part of HICE is that you don't have to go to all this hassle on the Excel sheet. You can assume diameter on a meter, like 3 meter, for example. And then quick size. And we need to give you everything. The total volume you need it for such a flow rate, the diameter and the length and the liquid height. If it is a flat cylinder, horizontal, of a less hemisphere, for example, if it is ellipsoidal head, you can choose whatever. For me, I love the hemisphere, which is easy for the mechanical engineer. Then we need to enable weir. Okay, thank you. Then the nozzles are calculated based on the diameter, the length, the base elevations, the diameter for the gas well, the stream nozzle. It is high from the bottom of the vessel 0.7, elevation 0.7, 100%. This is the condensate. We will take it from 0.127 from the bottom of the vessel. The same for water, we will take it from the zero from the top bottom of the vessel. Heat losses, we don't need any insulation for a separator. Don't have any problem with the heat losses. Then the level tabs, you can put the level tabs you want. Level transmitter, what process variable high, process variable low, 0 for the level, 0 to 100%, and location at chamber 1. This all for me? No. Let's close this and make it quick sizing for a control valve. Install control valve, then sizing it, then we will finish today. Here is the home. Sorry, flow sheet. As it is. Right connection. Hammer, can you please press F4? Press F4. F4.
F4. Okay.
Not okay. Nothing happened.
Now.
Finally, alhamdulillah.
Alhamdulillah.
What we are going to do is to select a control valve. This is control valve. We are going to connect. Now I connect the control valve. What's condensate coming out of the three-phase separator is going to the valve. What is going out of from the valve is going to the surge drum. The good part is that outlet 1 here, the inlet a pressure of 16 bar G, and I understand that this surge drum will work at 150 BSIG, BSIA. Now the control valve is solving, have no problem. For me, the most, here is the linear, here is the quick opening, here is the equal percentage. For me, size valve solve all these issues to get the most critical part for any instrumentation engineer wanted from me is the CV. How much liquid will pass through the opening of this valve in case we have a design pressure 16 at this stage and 9.3 at this stage. This is coming from the rating tab where we can print for 4.8 US gallon per minute, which is the standard condition at CVs. This is the control valve sizing, that is the separator sizing. So both can be done on Excel sheets, yes. That's all for me. You got my question, you got what I want to say, guys, or you have a headache? Muhammad, yes.
Yes, doctor, yes.
How is the headache?
No, it's okay.
Okay. Naja,
Yeah, it's good. So only we specified the outlet pressure and it configured everything, correct?
yes, this is the beautiful of the HYSYS.
So rating tab, we need to put all these things in rating, correct? Rating
So,
tab.
Rating
we
tab,
need to-
yes. Rating tab solve all of this.
Okay.
Phase,
Yes, please.
did you see how we sizing the control valve? How we sizing the separator?
Yes, the valve is straightforward.
Yes.
The separator, I'm not sure what are the mandatory input in case of HYSYS. Instead, in case of Aspen, I mean.
I don't get your point. What do you mean?
The must input for the Aspen to run the Aspen for the separator.
Just define the stream and put the surge time. Nothing else.
The surge time and what else?
The stream itself.
Oh, the stream
Yes.
condition. Okay.
Nothing else. You get the length and the diameter. Based on that, you can judge whatever you want. Do you have a simulation for your plant, Muhammad? Faiz, sorry. Faiz.
Yes, in the past we used to have a simulation in the plant where I was working,
Okay.
but it is not used. Honestly speaking, not used very frequent.
Okay. Anyhow, you should have one at least to judge your plant performance as a typical operation. Thanks everyone for today. Naja, do you have any question? Faiz, Muhammad, anyone have a question?
Just Doctor, I was able to download the download completed for the S-Pen. So I need your support really to complete the installation.
I will join you on the team viewer. Just give me a minute. Naja, do you have any problem for today? Any questions?
No, doctor. Thank you very much.
You're welcome. Muhammad?
Yeah, thank you, Doctor, for your efforts. Much appreciated. In fact, I have a question, but if you are just tired or something, we can make it the next week, inshallah.
No. You just ask. Don't worry.
Yeah, thank you very much. Thank you. In fact, I just didn't get the idea regarding the high pressure and low pressure, please. In fact, the internet was interrupted and the voice was breaking, so for this reason, I didn't follow it. How did you?
What
Thank you very much.
What we are afraid of? We are afraid for two things. The pressure getting high, so this vessel can get ruptured. This is why we have the high tripping system to stop any feed from entering the separator to make the explosion happen. This one case. On the other case, why we put the low, because, for example, if the gas line out of the separator, the gas line which is getting out of the separator, or any equipment downstream of the separator, have a failure or rupture, your pipeline have a big leak, massive leak. The pressure inside the separator will go down. If we didn't put low to stop it, this means the leak will continue forever. We will not stop the leaking. We have to manually intervening to close this leak, which is not the case, which is not right. So based on that, low will happen, separator will trip until you correct the leak. Then you restore your operation again. You got it or not?
Yes, doctor. So there is no just like intervention from the SIS or something like this. It depends on the maintenance activities and such things.
No, the SIS will intervene when there is a leak. When there is low, this
Yes.
pressure low will close the inlet of the separator.
So you mean inside the pipeline, for example, downstream the separator.
Yes.
So if there is a rupture, okay, so there will be an increase,
Decrease.
just like reduction in the pressure, decrease in the pressure of the separator itself, right?
Yes, totally right. The pressure inside the separator will decrease and it will feed the rupture.
In this case, the shutdown valve on that pipeline will take the action.
Which pipeline you think friction will happen?
Let's say, for example, the condensate one.
You can't judge which piping will have the rupture. That's why you are always connecting the low to the inlet of the separator. Wherever the friction downstream the separator, it will close the inlet. You get my point?
Yeah, so the inlet shutdown valve will be responsible for such action.
Yes, totally right.
And just wanted to ask you about if when there is an alarm, okay? So alarm is not connected to, for example, the shutdown valve or something like this. I just wanted to understand the mechanism, how when for moving for the layer of protection. So when there is high, the alarm will just like give us audible or just like visual warning.
High, you will get the
And
alarm.
how
You will get the alarm.
high, okay. So no action has been, for example, in terms of level, it still increases. So when it reach high, so yeah, there is shutdown valve. So for the separator itself, so you mean the level 1, which is the ESD connected to the level 1 on high, will take the action to just like.
I don't get your point. High
Yes,
alarm.
in fact, I can't accept.
Let-
If you can just, or it's still my screen, right, Doctor?
yes.
Yeah. So you see the PID now.
No, I see the HISES. Can you share? Just share again. Share European ID. Yes. Now share European ID. Yes, tell me.
You can see it now.
Yes.
Yeah. So for example, in this case, okay. So now when it reaches to the high level, so it will take action or send signal to the ESD. Okay.
Yes.
Now here. So how, this is what I didn't understand. How, just like, for example, will it close this ESD or open, or how can control the other ESDs and
Normally, Muhammad.
just like let's
Yeah,
say what happened next? We reached the high and this is the ESD. What happened next, please?
High for the level. Normally close the branch
Yeah.
of the liquid. Normally close
Okay.
the branch of the liquid. High, if we have a high, the problem is that this
Yes.
liquid will go to the gas way, right?
Yeah.
We are afraid from this. We want to prevent this from happening. So, what we are trying to do is to isolate all the equipment, all the exits of this equipment, exits and inlets for this equipment. Now, let's see. The inlet, we will close it. The outlet for the gas, we will close it. The outlet for the liquid condensate, we will close it. The outlet for the liquid water, we will close it. The blue down, we will keep it closed for a high liquid, because we don't want to release the gas. We don't want to lose our production. What we were going to do, we simply will drain the level. We will drain the level to the closed drain, where we can restore back the liquids. Once we reach the level, normal level, we can start up again. This is for the high. No, we can drain it from the left, the manual valve on the bottom.
Can you take the control, Doctor, please?
Okay.
So you mean this will be closed and this valve will be closed, right? These two?
This valve is open. This one is open.
Okay.
And
Okay.
liquid is running this way, the normal way, right?
Yes.
Now, I have a problem on the liquid level. So, this valve was closed first
Yes.
as an interlock activated. Now I will go to open this one and this one and drain all the way to the closed drain.
Yes.
This such easy. This is the easiest part. This is a typical operation behavior.
Yeah, thank you. But let me just show. I mean, when it reaches here, so what is the connection between the ESD here and between the others? For example, here there is interlock, so which can close or open, right?
Okay, this high when it activated, it will simply send the signal to the ESD? No, it will send the signal to the
Yeah.
DCS, the controlling room.
Okay.
The control room, when he receives this signal, automatically will activate the interlock. The interlock will come here to kick in. 1, 2, 3 at the inlet, 4 here, bottom 5.
According to the cause and effect diagram that specify the activity should be taken in each case.
You. That's why we
Yeah.
are interesting with the philosophies. Philosophy is telling
Yes.
you how your process engineer will think about this one. And based on how he's thinking, he bought the cause and effect. That's why you cannot review the cause and effect without knowing all the philosophy judging your equipment.
Yes, yeah. Thank you very much. Much appreciated.
Welcome. Thank you. Seeing you next week, inshallah.
Inshallah, Doctor. Thank you for your efforts. Much appreciated. Thank you.
Welcome.
Thank you very much.
Welcome. Faiz, keep with
Can you
me.
please
Yes,
just share the Excel sheet with us, if possible, please?
yes, sir. Without saying, already you have all
Thank
the
you.
new revision calculation on the Google Drive, but I will share it. What I just make it now.
Inshallah. Thank you very much.
Welcome.
Jazakallah khair.
جزاكم الله.